dynamics of galactic cores. Unlike the Milky Way, Andromeda's spiral arms are relatively well-defined, giving it a classic pinwheel appearance. These arms are teeming with regions of active star formation, where immense clouds of hydrogen gas collapse under their own gravity to form new stars. The galaxy's bright blue clusters, seen in ultraviolet light, are a testament to the ongoing birth of short-lived stars that will eventually explode as supernovae. The older, reddish stars in Andromeda's halo and central bulge tell a different story, one of ancient star systems that have weathered billions of years. These populations provide a glimpse into the early epochs of galactic evolution, helping scientists piece together the history of star formation in our local universe. Perhaps the most tantalizing of the Andromeda is its impending collision with the Milky Way. Observations reveal that Andromeda is hurtling toward us at a speed of about 110 kilometers per second. In approximately 4.5 billion years, the two galaxies are expected to merge in a spectacular cosmic dance, forming a new elliptical galaxy, sometimes referred to as Milkomeda. This collision will be a transformative event, reshaping the structure of both galaxies and igniting a burst as gas and dust clouds collide. Although such a cataclysm might sound destructive, the vast distances between stars mean that directs are unlikely. Instead, the merger will create tidal tails, intricate streams of stars, and a dramatic reshuffling of galactic components. Andromeda has been studied extensively using both ground-based and space-based telescopes. The Hubble Space Telescope has provided breathtaking images of the galaxy, revealing its intricate spiral structure, star-forming regions, and even individuals. Future observations such as the JACE telescope and the extremely large telescope promise to deepen our understanding of Andromeda by studying its stars, planets, and black hole in unprecedented detail. One of the most exciting areas of research involves the search for exoplanets in Andromeda. While detecting planets in another galaxy is extraordinarily challenging, advancements in microlensing techniques and spectroscopy may one day allow us to identify worlds orbiting stars in this neighboring galaxy. Such discoveries could revolutionize our planetary systems and the potential for life beyond the Milky Way. Andromeda's proximity to reference point galaxies throughout the universe. By examining its structure, composition, and dynamics, astronomers can develop models that apply to galaxies billions of light years away. The study of Andromeda's dark matter halo, for instance, has implications for understanding the mysterious substance that makes up 85% of the universe's mass. It also serves as a time capsule, preserving evidence of past interactions with other galaxies. Stellar streams, faint trails of stars torn from satellite galaxies, crisscross Andromeda's halo, offering clues about its history of galactic cannibalism. These remnants of past astronomers reconstruct the timeline of Andromeda's growth, providing a glimpse into the life cycle of galaxies. Beyond its scientific value, the Andromeda galaxy has an imagination for centuries. Visible to the naked eye as a faint smudge in the night sky, inspired countless myths and dreams of intergalactic travel. As our technology advances and our understanding of the cosmos deepens, Andromeda remains a symbol of humanity's insatiable curiosity and our quest to comprehend the universe. Whether through the lens of a telescope or the imagination of a dreamer, the Andromeda galaxy invites us to ponder profound questions about our place in the cosmos. What stories do its stars tell? What secrets lie hidden within the expanse? And what future awaits as our two galaxies converge in a cosmic embrace? The Andromeda Galaxy, or Messier 31, stands as one of the most intriguing and vital cosmic neighbors of the Milky Way. Its staggering proximity of 2.5 million light-years allows astronomers to explore its intricate structure with unprecedented clarity, a window into the processes that govern galaxies across the Spiral Galaxy, over 220,000 light-years in diameter, surpasses our own Milky Way in size and contains an estimated 1 trillion stars. Its colossal mass and dynamic nature make it a perfect laboratory for studying galaxy formation, star evolution, and the mysterious force of dark matter. Its double nucleus, a feature visible in its central bulge, has perplexed scientists for decades. Peculiar structure hints history of mergers and interactions with smaller galaxies. At its core lies a supermassive black hole, approximately 140 million times the mass of the Sun. This black hole exerts a gravitational pull that influences the orbits of nearby stars and triggers high energies such as X-ray flares. These intense bursts of radiation illuminate the dynamic and sometimes violent that occur in galactic cores. Collapse under gravity to form new stars. Bright blue clusters dot these arms, signifying the presence of massive, young stars that shine intensely before exhausting their fuel and ending their lives in spectacular supernovae. These explosions enrich the galaxy with heavy. The spiral arms of this galactic giant are regions of immense activity, where dense molecular elements, driving the chemical evolution necessary for the formation of planets and, potentially, life. The interstellar medium of Andromeda is also rich with hydrogen gas and cosmic dust, creating vibrant nebulae that serve as the birthplaces of new stars. Unlike our Milky Way, which exhibits a more subtle spiral pattern, Andromeda's arms are well defined, giving it the iconic shape often associated with galaxies. These arms are not static. They are shaped and reshaped by the gravitational interactions with Andromeda's satellite galaxies. Observations reveal that Andromeda is surrounded by a swarm of smaller galaxies, some of which are being torn apart by its gravitational pull. These interactions create streams of stars, known as type, that arc through Andromeda, providing clues about its history of mergers and acquisitions. Andromeda is not only a showcase of stellar life and death, but also a treasure trove of ancient stars. Its halo contains some of the oldest stars known, remnants from the earliest epochs of galactic formation. Studying these ancient stellar populations, scientists trace the history of Andromeda back billions of years, uncovering the conditions that prevailed when the universe was young. These studies also know the processes that shaped our own galaxy, offering a broader context for the evolution of the cosmos. One of the most captivating aspects of Andromeda is its future collision with the Milky Way. Observations of its motion indicate that it is hurtling toward us at a speed of approximately 110 kilometers per second. In about 4.5 billion years, the two galaxies will collide and merge to form a larger galaxy. This event, often galactic dance, will dramatically reshape the structure of both galaxies. Stars, gas, and dark matter will be redistributed in a complex of gravitational forces, creating tidal streams and igniting bursts of star formation. Despite the seeming violence of such a merger, the vast distances between individual stars mean that direct collisions between them are unlikely. Instead, the merger will create a new, sometimes referred to as Andromeda, with an elliptical structure and a new center of mass. The Andromeda galaxy has been the focus of numerous scientific missions and observations. The Hubble Space Telescope has provided some of the most detailed images of its structure, capturing its spiral arms, central bulge, and outer halo with stunning clarity. These observations have not only deepened our understanding of Andromeda but also served as a benchmark for studying other spiral galaxies in the universe. Advanced instruments, such as the James Webb Space Telescope, promise to unveil even more secrets, allowing astronomers to study the galaxy's individual stars, planetary systems, and even its dark matter halo with unprecedented. The search for exoplanets within Andromeda is a burgeoning field of study. While detecting planets in sea is extraordinarily challenging, such as gravitational microlensing offer a glimpse into this possibility. These methods rely on the bending of light caused by the gravitational field of a planet or star, revealing the presence of celestial objects that would otherwise remain hidden. Discovering exoplanets could our understanding formation, potentially revealing worlds vastly different from those in the Milky Way. Andromeda's immense halo of dark matter extends far beyond its visible disk, influencing the motion of its stars and satellite galaxies. This unseen component constitutes the majority of the galaxy's mass, yet its nature remains one of the greatest mysteries in astrophysics. By studying the distribution and behavior of dark matter in Andromeda, scientists hope to unlock the secrets of this enigmatic substance, which plays a crucial role in galaxies. As the largest galaxy in our local group, Andromeda serves as a cosmic mirror, reflecting the processes principles that govern galaxies on larger scales. Its intricate structure, active star-forming regions, and dynamic interactions with other galaxies provide a microcosm of the universe's complexity. By studying Andromeda, astronomers gain insights into phenomena that apply to galaxies of light years away, bridging the gap between our local universe and the distant cosmos. The Andromeda galaxy is not just an object of scientific inquiry, it's inspiration and wonder. Its visibility to the naked eye as a faint smudge in the night sky has captivated observers for centuries, from ancient astronomers who catalogued it as a nebula to modern scientists who unravel its mysteries with cutting-edge technology. Andromeda represents humanity's end to understand the cosmos, a curious nation. The Andromeda galaxy is a beacon of cosmic curiosity, continuously drawing the gaze of astronomers and dreamers alike. Its vastness and complexity defy easy understanding, inviting deeper exploration with every new discovery. The galactic giant is not just a collection of stars, gas, and dark matter, it is a storybook of the universe itself, containing chapters that span billions of years and countless transformations. The study of Andromeda has provided humanity with unparalleled insights into the life cycles. Proximity makes it an ideal target, as we can observe its individual stars and clusters with remarkable clarity. Scientists have interstellar populations within Andromeda, each with unique characteristics and histories. From the bright, young blue stars of its spiral arms to the ancient red stars in its halo, every stellar population tells a different part of the galaxy's story. These stars are not just cosmic objects, they are timekeepers, offering clues about the conditions that shaped Andromeda over its lifetime. Andromeda's history is written in the light of its stars, but it is also etched in the faint streams of material that surround it. These tidal streams are the remnants of smaller galaxies that were torn apart and absorbed by Andromeda's gravity. By mapping these streams, astronomers can reconstruct the galaxy's dynamic past, seismic interactions that have shaped its. It presents a merger, a collision, or a gravitational tug-of-war that occurred millions or even billions of years ago. Together, they form a mosaic of Andromeda's evolutionary journey, providing a glimpse into the violent processes that drive galactic growth. The role of dark matter in Andromeda's formation and evolution cannot be overstated. This invisible, enigmatic substance makes up the majority of the galaxy's mass, yet its true nature remains one of the greatest unsolved mysteries in modern science. Dark matter or absorb light, making it undetectable means. However, is inferred from its gravitational effects on visible matter. The dark matter is a halo that stretches far beyond the galaxy's luminous disk, influencing the motion of its stars and satellite galaxies. By studying the distribution and behavior of dark matter in Andromeda, scientists hope to clues about the fundamental composition of the universe itself. Andromeda's future is as fascinating as its past. The impending collision with the Milky Way is not just an event of local significance, it is a cosmic spectacle that will reshape the local group of galaxies. This merger will occur over billions of years, beginning with subtle gravitational interactions that will distort the shapes of both galaxies. As the two spiral galaxies draw closer, their stars will form tidal bridges, connecting the two systems in a gravitational embrace. Gas clouds will collide, triggering bursts of star formation and creating brilliant nebulae that will light up the night skies of any planets within these galaxies. Eventually, the two galaxies will merge into a single, massive elliptical galaxy, a testament to the transformative power of gravity on cosmic scales. While the prospect of this collision may seem daunting, it is a reminder of the changing nature of the galaxies are islands of stars. They are constantly interacting, merging, and evolving. The Andromeda-Milky Way collision may reshape the structure of these galaxies but also provide a unique opportunity to study the processes that drive galactic evolution. For astronomers billions of years in the future, this event will be a natural laboratory for understanding the interplay of gravity, dark matter, and interstellar gas. The Andromeda Galaxy has also inspired humanity to think beyond our own cosmic neighborhood. The possibility of Andromeda, while purely speculative, raises profound questions about the nature of the universe and our place within it. If planets orbit stars in Andromeda, and there is no reason to believe they do not, then the potential for life beyond the Milky Way becomes a tantalizing prospect. While the vast distances between galaxies make direct exploration unlikely for the foreseeable future, the study of Andromeda fuels our imagination and drives the development of new technologies that may one day bring us closer to answering these questions. Telescopes have played a crucial role in our understanding of Andromeda, transforming it from a faint smudge in the night sky to one of the most studied objects in the universe. Ground-based observatories equipped with advanced adaptive optic systems have provided detailed views of the galaxy's structure, while space-based telescopes like Hubble have captured breathtaking images that reveal its intricate beauty. These observations have not only deepened our understanding of Andromeda but also served as a benchmark for studying other galaxies. By comparing Andromeda to galaxies at various distances, astronomers can piece together a timeline of cosmic history, tracing the evolution of galaxies from the early universe to the present day. Andromeda's spiral arms, central bulge, and halo are all areas of active research, each offering unique insights into the workings of galaxies. The spiral arms are regions of intense star formation, where massive stars light up the surrounding gas and dust, creating some of the most beautiful and dynamic regions in the galaxy. The central bulge, is dominated by older stars, providing a window into the galaxy's past. The halo, with its sparse population of ancient stars and globular clusters, represents the remnants of Andromeda's earliest epochs, a fossil record of the galaxy's formation and growth. As we continue to study Andromeda, we are reminded of the interconnectedness of all things in the universe. The same processes that shape this distant galaxy, the Milky Way, and countless. By studying Andromeda, we gain a deeper understanding of our own galaxy, our place in the cosmos, and the forces that govern the universe. The Andromeda Galaxy stands as a pillar of scientific curiosity and inquiry, revealing profound truths about the universe's structure and evolution. Each observation, each analysis of this celestial neighbor deepens our understanding of the intricate forces that shape galaxies, including our own Milky Way. Scientists and astronomers have spent decades unraveling its mysteries, from its unique physical characteristics to the secrets hidden in its dark matter halo, which stretches far beyond its visible edges. To expand the horizon of understanding Andromeda, we delve even deeper into the vast scientific details that define this monumental galaxy. One of the key features of Andromeda is its massive dark matter halo, a structure so vast and diffuse that it dominates the dynamics of the galaxy. Observations suggest that this halo extends hundreds of thousands of light-years beyond the Ignis disk, encompassing both its satellite galaxies and intergalactic space. Unlike the stars and gas within the galaxy, dark matter does not interact with electromagnetic forces, making it invisible to telescopes. However, its gravitational effects are profound. The motion of stars in Andromeda's outer regions can only be explained if we account for the gravitational influence of this unseen mass. The study of Andromeda's dark matter halo has significant implications for cosmology. By measuring its distribution density, astronomers can test theories about the formation of large-scale structures in the universe. The presence of such a massive halo supports the lambda CDM, lambda cold dark matter, model, which posits that galaxies form within vast, invisible scaffolds of dark matter. Furthermore, detailed mapping of Andromeda's halo through gravitational lensing and stellar dynamics provides clues about the nature of dark matter particles, one of the most elusive questions in modern physics. Another remarkable aspect of Andromeda is its double nucleus, a feature that has fascinated scientists since its discovery. This central region contains two distinct clusters of stars, separated by only a few light years. The prevailing hypothesis is that one of these clusters represents a dense group of stars surrounding Andromeda's supermassive black hole, while the other is a remnant of a smaller galaxy that merged with Andromeda long ago. This unusual configuration offers a unique opportunity to study the dynamics of galactic nuclei and the behavior of stars in extreme gravitational environments. The soup hole at the center of Andromeda is estimated to be about 140 million times the mass of the Sun, significantly larger than the black hole at the center of the Milky Way. This immense gravitational powerhouse shapes the orbits of stars within the galaxy's central bulge and influences the flow of interstellar gas. Observing the interactions between this black hole and its surroundings provides critical data for understanding the growth and evolution of supermassive black holes across the universe. These observations also help astronomers explore the relationship between black holes and galaxies, a fundamental question for physics. Andromeda's satellite galaxies add another layer of complexity to its story. These smaller galaxies, such as M32 and M110, orbit Andromeda in intricate patterns, influenced by its massive gravitational pull. Some of these satellites are in the process of being torn apart, their stars and gas streams forming tidal tails that arc across the sky. These interactions offer a glimpse into the nature of galaxy formation, where larger systems grow by accreting smaller ones. By studying these satellites and their interactions with Andromeda, scientists can reconstruct the galaxy's merger history, tracing its growth over billions of years. The star-forming regions within Andromeda are particularly noteworthy for their scientific importance. These areas, known as HII regions, are dense clouds of ionized hydrogen where new stars are born. Observations of these regions provide valuable insights into the processes that govern star formation, such as the role of magnetic fields, turbulence, and feedback from massive stars. The distribution and intensity of star-forming regions within Andromeda also shed light on the dynamics of spiral galaxies, revealing how density waves and gravitational interactions shape their structure. Andromeda's globular clusters, ancient spherical collections of stars, are another key area of research. These clusters, which orbit the galaxy in its halo, are among the oldest objects in the universe, with ages exceeding 10 billion years. By studying the chemical motion of these clusters, astronomers the conditions that prevailed in the universe when Andromeda was forming. Some globular clusters in Andromeda are thought to have originated in smaller galaxies that were later absorbed by the larger system, providing further evidence of its dynamic and turbulent history. One of the most exciting fields of research involving Andromeda is the search for exoplanets within its borders. While detecting planets in another galaxy is extraordinarily challenging, advancements in observational techniques have made this possibility increasingly feasible. For example, gravitational microlensing, a phenomenon where a Big bends and mag of a more distant star, can be used to detect planets in it. If successful, these efforts could reveal the first evidence of planetary systems beyond the Milky Way, offering a new frontier for the study of exoplanets and the potential for life elsewhere in the universe. The impending collision between Andromeda and the Milky Way is one of the most significant events in the galaxy's future. As the two galaxies approach each other, their gravitational interactions will initiate a complex series of events that will reshape both systems. Gas clouds will collide, triggering bursts of star formation that will light up the night sky. Spiral arms will be torn apart, forming tidal streams and bridges of stars. Over billions of years, the two galaxies will merge into a single, massive elliptical galaxy. Simulations of this process provide a detailed look at how such merge hold, offering a view on the long-term evolution of galaxies. The study of Andromeda extends beyond the visible spectrum. Observations in infrared, ultraviolet, and X-ray wavelengths have revealed phenomena that are invisible to the human eye. Infrared studies, for example, penetrate the dust clouds within Andromeda, uncovering regions of intense star formation and the distribution of cooler stars. Ultraviolet observations highlight the youngest and hottest stars, while X-ray studies detect high-energy processes near the galaxy's supermassive black hole and in its dynamic star-forming regions. Together, these observations provide a multi-wavelength view of Andromeda, allowing astronomers to build a comprehensive picture of its structure and activity. Andromeda continues to inspire not only scientists but also the broader public, serving as a symbol of humanity's quest to explore and understand the universe. Its presence in the night sky, visible as a faint smudge to the naked eye, connects us to the vastness of the cosmos, of our place within it. Through telescopes and spacecraft, we have transformed this distant neighbor from an object of curiosity into a cornerstone of modern astrophysics, a testament to the power of human ingenuity and imagination. The Andromeda Galaxy is more than just a spiral of stars, gas, and dust. It is a dynamic system governed by complex physical processes that stretch the boundaries of our understanding. Each layer of Andromeda, from its luminous core to its diffuse halo, offers a wealth of information about the forces shaping galaxies, the origins of the universe, and the interconnected nature of cosmic structures. To truly appreciate the depth of Andromeda's scientific significance, we must dive further into its intricate details, probing the mechanisms that govern its past, present, and future. One of the most intriguing phenomena in Andromeda is the ongoing interaction between its stars and interstellar medium, ISM. The ISM is a mixture of gas, dust, and plasma that permeates the galaxy, acting as the raw material for star formation. Andromeda's ISM is highly structured, forming filamentary clouds, dense clumps, and expansive regions of ionized gas. Observations of the ISM reveal the complex interplay between gravity, magnetic fields, and feedback from stellar winds and supernovae. These processes regulate the galaxy's star formation rate, determining how efficiently Andromeda converts gas into stars over time. Star formation within Andromeda is not uniform. It is concentrated in specific regions, particularly along the spiral arms. These arms are sites of enhanced density, where shock waves from density waves compress gas clouds, triggering gravitational collapse. The role of density waves in spiral galaxies like Andromeda has been a subject of extensive study, as they provide a framework for understanding the long-lived spiral patterns observed in galaxies. These waves are essentially gravitational oscillations that propagate through the disk of the galaxy, concentrating stars and gas into spiral patterns without the material itself permanently remaining in the arms. This dynamic structure ensures a steady cycle of star formation and dispersal. The star formation process itself is driven by a delicate balance of forces. Gravity works to collapse gas clouds, forming protostars, while thermal pressure, turbulence, and magnetic fields resist collapse. In Andromeda, regions of active star formation are often accompanied by intense feedback from massive stars. These stars emit powerful ultraviolet radiation, which ionizes the surrounding gas, creating glowing nebulae known as HII regions. As these stars reach the end of their lives, they explode as supernovae, releasing vast amounts of energy and enriching the ISM with heavy elements. This enrichment is a critical step in the chemical evolution of galaxies, as it provides the building blocks for planets and life. The chemical composition of Andromeda's stars and ISM offers insights into its history of star formation and mergers. Spectroscopic studies reveal a gradient in metallicity, the abundance of elements heavier than hydrogen and helium across the galaxy. The central bulge, which contains older stars, has a higher metallicity, reflecting a history of intense star formation in the galaxy's early years. In contrast, the outer regions of the disk and halo have lower metallicity, suggesting a slower rate of chemical enrichment. This gradient is a fingerprint of the processes that have shaped Andromeda over billions of years, from its initial collapse to its interactions with other galaxies. Andromeda's globular clusters are another rich source of information about its chemical and dynamical history. These dense collections of stars are among the oldest objects in the galaxy, with ages often exceeding 10 billion years. By studying the motions and compositions of these clusters, astronomers can reconstruct the conditions that prevailed when Andromeda was forming. Some globular clusters exhibit unusual properties, such as retrograde orbits or distinct chemical signatures, suggesting that they originated in smaller galaxies that were later accreted by Andromeda. They support the hierarchical model of galaxy formation, in which large galaxies grow through the assimilation of smaller systems. Beyond its visible components, Andromeda's structure is profoundly influenced by its dark matter halo. This halo, which extends far beyond the galaxy's disk, dominates its mass and shapes the motion of stars and satellite galaxies. By measuring the rotation curve of Andromeda, how the orbital speed of stars varies with distance from the center, astronomers have inferred the presence and distribution of dark matter. The flatness of the rotation curve at large distances, where visible matter becomes sparse, is a clear indication of the gravitational influence of dark matter. This discovery has been pivotal in the development of modern cosmology, highlighting the importance of unseen components in shaping the universe. The relationship between Andromeda and its satellite galaxies is another area of intense study. These smaller systems, such as M32, M110, and others, are bound to Andromeda by its gravitational pull, forming a miniature ecosystem within the local group. Some of these satellites are in the process of being disrupted, their stars forming tidal streams that weave through Andromeda's halo. These streams provide a snapshot of galactic cannibalism in action, illustrating how large galaxies grow by accreting smaller ones. By mapping these streams, astronomers can reconstruct the orbits of the disrupted galaxies, revealing the history of their interactions with Andromeda. The study of Andromeda extends beyond its stars and dark matter to its population of supermassive black holes, neutron stars, and other exotic objects. The central black hole, with a mass of 140 million suns, is a key galaxy's core. This black hole influences the orbits of nearby stars and may play a role in regulating the flow of gas into the central regions. Observations of X-ray and radio emissions from the core provide clues about the activity of this black hole, which is currently in a relatively quiescent state. Future observations may reveal periods of increased activity, such as flares caused by the accretion of matter. Andromeda's neutron stars and stellar mass black holes are remnants of massive stars that have completed their life cycles. These objects are often found in binary systems, where they accrete matter from a companion star. As this matter falls onto the compact object, it releases energy in the form of X-rays, creating some of the brightest sources in the galaxy. Studying these systems in Andromeda provides insights into the end stages of stellar evolution and the dynamics of binary systems. The future of Andromeda is perhaps its most captivating aspect. Its collision with the Milky Way will mark a new chapter in the history of both galaxies, reshaping their structures and forming a new cosmic entity. Simulations of this merger reveal the complex interplay of gravitational forces, which will tear apart the spiral arms, create tidal bridges and streams, and trigger bursts of star formation. Over billions of years, the two galaxies will settle into a massive elliptical galaxy, a testament to the dynamic and interconnected nature of the cosmos. As we probe deeper into the Andromeda galaxy, it becomes increasingly clear that this celestial neighbor is not just an isolated system but a microcosm. Its intricate structure, dynamic interactions, and rich history make it a cornerstone of modern astrophysics, offering answers to some of the most profound questions about the nature of and the forces that govern the cosmos. The Andromeda galaxy, our closest galactic neighbor, is not just a vast collection of stars, gas, and dark matter. It's a living laboratory where the secrets of the universe are constantly unfolding. Every corner of this colossal spiral galaxy, from its glittering core to its faint outer halo, holds stories of creation, destruction, and rebirth on a scale that challenges the limits of human imagination. At the heart of Andromeda's mysteries lies a component we cannot see: dark matter. This enigmatic substance, which makes up most of the galaxy's mass, doesn't emit light, heat, or any detectable radiation. Instead, we infer its presence through its gravitational influence on the galaxy's stars and gas. Without dark matter, Andromeda's majestic spiral arms wouldn't hold together. They would have unraveled long ago. Dark matter forms a vast, invisible halo around Andromeda, extending hundreds of thousands of light-years beyond its visible disk. The gravity of this halo acts as scaffolding, pulling stars, gas, and dust into the familiar spiral structure we observe today. Mapping this halo is one of the most exciting challenges in astrophysics. Using gravitational lensing, a phenomenon where dark matter bends the light of background objects, astronomers are beginning to trace its contours, revealing a hidden architecture that underpins the galaxy. This work isn't just about understanding Andromeda. Dark matter halos like this exist around all galaxies, and by studying the closest example, we gain insight into the invisible framework that shaped the entire universe. Andromeda's core is unlike anything in the Milky Way. At its center lies not one, but two dense clusters of stars, a double nucleus. One cluster orbits a supermassive black hole that's 140 million times the mass of the Sun. The other, offset slightly, might be the remnants of a smaller galaxy swallowed by Andromeda in the distant past. Why does Andromeda have two nuclei? One hypothesis is that the second cluster is the ghost of a galactic collision. Billions of years ago, Andromeda likely devoured a smaller galaxy, and its core didn't disintegrate entirely. It became trapped, orbiting within Andromeda's gravitational well. Over time, these two clusters will likely merge, adding to the already extraordinary mass of the central black hole. Andromeda's spiral arms are bustling regions of activity where stars are born. These arms are shaped by waves of density, essentially gravitational traffic jams. As gas clouds enter these high-density regions, they slow down, compress, and ignite in bursts of star formation. Massive blue stars, some tens of times the mass of the Sun, dominate these regions, shining brightly but living short, fiery lives before exploding as supernovae. These explosions are cosmic recycling events. They scatter heavy elements, like carbon, oxygen, and iron, into the surrounding space, enriching the galaxy's interstellar medium. Without these elements, planets like Earth and life as we know it couldn't exist. In a way, Andromeda's star-forming regions are factories producing the raw materials for future worlds. Beyond its bright core and spiral arms lies Andromeda's halo, a dim, extended region filled with ancient stars and faint remnants of past collisions. This halo is a treasure to archaeologists, astronomers who reconstruct the history of galaxies by studying their structures and stellar populations. One of the most fascinating features in Andromeda's halo is its stellar streams, long, faint trails of stars left behind by smaller galaxies has absorbed of years. These streams are cosmic fossils, preserving the memory of galactic mergers. By mapping these trails, astronomers can recreate Andromeda's growth history, revealing a violent past of collisions and cannibalism. The largest and most famous of these streams is the giant stellar stream, a 100,000 light-year-long ribbon of stars thought to be the remains of a once massive satellite galaxy. Studying these structures helps scientists understand not just Andromeda's history, but also how galaxies like the Milky Way grow through mergers and accretion. Perhaps the most dramatic chapter in Andromeda's story is yet to come. Observations show that Andromeda is hurtling toward the Milky Way at a speed of 100 km per second. In about 4.5 billion years, the two galaxies will collide in a cosmic event that will reshape the local group of galaxies forever. What will happen during this collision? As the galaxies approach, their gravitational forces will pull at each other, distorting their shapes and flinging stars into long tidal tails. Gas clouds will collide, sparking bursts of star formation on an unprecedented scale. Over time, the two galaxies will merge into a single, massive elliptical galaxy named Milky Way. Despite the scale of this, individual stars are unlikely to collide due to the vast distances between them. Instead, the collision will create a spectacular light show, with new stars igniting in tidal streams, painting the night sky. Andromeda's stars likely host countless planets, yet we've only just begun to explore this possibility. Detecting planets in another galaxy is an extraordinary challenge, but techniques like gravitational are opening new doors. Microlensing occurs when a massive object passes in front of a barrier, magnifying its light and revealing the presence of orbiting planets. If planets are found in Andromeda, they could be vastly different from those in the Milky Way environment. Some might orbit stars in dense clusters, experiencing a sky filled with thousands of brilliant suns. Others might have religion, circling stars on the edges of the galaxy's spiral arms. The discovery of exoplanets in Andromeda would not only expand our understanding of planetary systems, but also ignite the imagination, reminding us of the potential for life beyond our galactic borders. The Andromeda Galaxy is more than a cosmic neighbor, it is a gateway to understanding the universe itself. Its proximity allows us to study phenomena in distant galaxies but are too faint to observe in detail. By examining Andromeda's structure, star population fractions, we gain a clearer picture of its form, evolve, and eventually meet their fate. Andromeda is a living reminder of the connectedness of the cosmos. Its stars, much like those in our Milky Way, are born, live, and die in cycles that produce the elements necessary. Its halo, mysterious and invisible, binds it together, just as dark matter structures the universe on the largest scales. As we look toward Andromeda with ever-advancing telescopes and instruments, we are not just observing another galaxy, but into the mechanisms that govern the cosmos itself. And in its vastness, we are reminded of our small but significant place in this grand, unfolding story. Galaxy is a testament to the universe's complexity, a place where science converges with the unknown. Every new observation of its reveals a nuzzle of evolution shaping the cosmos. The galaxy's massive disk contains over 1 trillion stars, a stellar population far larger than that of the Milky Way. Within this stellar population, we find stars in every stage of their life cycle, from bright, young blue stars to ancient red giants that serve as time capsules from an earlier universe. This mixture of stars offers a unique opportunity to study how galaxies and change over billions of years. The interplay between stars and their surrounding environment is evident in Andromeda's disk. Its regions of active star formation are lit up by massive, short-lived stars whose intense ultraviolet radiation ionizes nearby gas cloud glowing nebulae. These regions are dynamic, constantly reshaped by the forces of stellar winds and supernova explosions. Such activity enriches the interstellar medium with heavier elements, providing the raw materials for the next generation of stars and planets. Beyond its spiral arms lies a much fainter halo of stars, globular clusters, and streams of debris from past galactic interactions. Though, extending hundreds of thousands of light-years from the galaxy's center, is a goldmine for understanding Andromeda's violent history. Stellar streams, such as the giant stellar stream, are remnants of smaller galaxies that Andromeda absorbed, a process that continues to this day. These streams are faint and difficult to detect, but their existence provides critical evidence of the hierarchical nature of galaxy formation, where larger systems grow through the smaller one. Andromeda lies its supermassive black hole, surrounded by a dense swarm of stars. This black hole, millions of times the mass of the Sun, is a region of intense gravitational forces. Stars in the vicinity of the black hole exhibit rapid orbital motions, a direct consequence of its immense mass. Currently in a relatively dormant state, this black hole has likely experienced periods of heightened activity, consuming nearby material and releasing amounts of energy. Observing these central regions offers a glimpse into the process in galactic phenomenon throughout the challenging to observe in distant galaxies. Andromeda's double nucleus adds another layer of intrigue to its central region. This structure, consisting of two closely separated clusters of stars, suggests a complex history of mergers and interactions. The hypothesis is that this feature represents the remnants of a smaller trapped in Andromeda's gravitational field after a past collision. Such findings illustrate the dynamic and ever-changing nature of galaxies, where interactions with neighbors leave lasting imprints on their structure. As we move outward from the core, these spiral arms showcase the intricate patterns formed by density waves. Not static structures but of increased density that rotate with the galaxy, compressing gas clouds and triggering star formation as they move. The arm's composition, a mix of bright young stars and dark interstellar dust, highlights the ongoing processes that sustain the galaxy's activity. Andromeda's relationship with its satellite galaxies further enriches its story. These smaller companions, such as M32 and M110, orbit within additional influence, and some are being actively disrupted. Tidal forces exerted by Andromeda pull stars and gas from these satellites, adding to the gas and leaving behind streams of debris. Observing these interactions helps astronomers understand how galaxies grow over time and how smaller systems contribute to the evolution of larger ones. The dark matter halo surrounding Andromeda is a dominant feature of its structure, far beyond its visible components. This halo, made of unseen material, accounts for the majority of the galaxy's mass. Its gravitational influence shapes stars and satellite galaxies and plays a crucial role in maintaining the spiral arms. The distribution of dark matter provides a critical test for theories about the nature of this mysterious substance and its role in the formation of large-scale cosmic structures. Andromeda's impending collision with the Milky Way is one of the most dramatic events in its future. As the two galaxies approach each other, their mutual gravitational pull will distort their shapes, creating tidal tails and bridges of stars. Gas clouds from both galaxies will collide, igniting bursts of stars will illuminate the night skies. Over billions of years, the two systems will merge, forming a massive elliptical galaxy. While such an event might seem catastrophic, the vast distances between individual stars mean that direct collisions are unlikely. Instead, the merger will result in a profound reshaping of both galaxies, a process that has occurred countless times throughout the universe's history. The study of Andromeda extends beyond visible light, with observations across the electromagnetic spectrum providing a more complete picture of its structure and activity. Infrared observations penetrate the dust in its spiral arms, revealing regions of active star formation. Ultraviolet light highlights young, massive stars, while X-ray emissions point to high-energy processes near the supermassive black hole and within binary star systems. Each wavelength reveals a different aspect of the galaxy, contributing to a comprehensive understanding of its nature. Andromeda's role in the local group of galaxies and its interactions with the Milky Way and its satellites. As the largest galaxy in this group, it exerts a significant gravitation, shaping the motions of neighboring galaxies. These interactions provide a scaled-down model of the processes that occur in larger galaxy clusters, where gravitational forces dominate the dynamics of the system. Studying Andromeda also offers a window into the conditions necessary for the formation of habitable planets and the potential for life beyond the Milky Way. While direct detection of exoplanets in Andromeda is not yet possible, models of planetary formation suggest that its stars likely host a diverse array of planets. If life exists elsewhere in the universe, studying nearby galaxies like Andromeda helps us understand the environments where it might thrive. The Andromeda galaxy, in its immense complexity and dynamic nature, stands as a microcosm of the universe itself. Its stars, gas, dark matter, and interactions with neighboring systems embody the forces that shape galaxies on all scales. As technology advances, our ability to study Andromeda will only deepen new insights in cosmos and our planet. Each discovery within Andromeda's borders reminds us of the intricate and interconnected nature of the universe, a tapestry woven from countless interactions over billions of years. The Andromeda galaxy's complexity extends into every observable component, providing endless avenues for scientific discovery. Its stars, spanning a wide range of ages and form the backbone of its luminous structure. By examining the light emitted by these stars, astronomers have gained a detailed understanding of their chemical ages and distribution throughout the galaxy. These stellar populations are grouped into distinct categories: the young, massive stars in the spiral arms, the older, metal-rich stars in the bulge, and the ancient, metal-poor stars in the halo. Each group tells a different chapter of Andromeda's history, revealing how the galaxy grew and evolved over time. The young stars in Andromeda's disk are concentrated in its spiral where conditions are ideal for star formation. These regions are shaped by density waves, which compress gas clouds as they travel through the disk. This compression triggers gravitational collapse, leading to the birth of new stars. Observing these regions allows scientists to study the initial stages of stellar evolution, from protostars to fully formed stars. The intense radiation from young, massive stars heats the surrounding gas, creating ionized bubbles that emit light across the electromagnetic spectrum. The older stars in Andromeda's bulge, by contrast, are remnants of the galaxy's early history. These stars formed during a period of intense star formation that occurred billions of years ago, likely fueled by the inflow of gas from the early universe. The bulge's stars are packed, orbiting the galaxy's center in a complex gravitational dance. The position reflects the conditions of the early universe, providing a glimpse into the processes that enriched the interstellar medium with heavy elements. Andromeda is some of the oldest stars in the galaxy, as well as a population of globular clusters that date back to its formation. These clusters, which contain hundreds of thousands of stars, are relics of the early universe, surviving relatively unchanged over billions of years. The motion and composition of these clusters offer clues about Andromeda's formation, suggesting that many of them originated in smaller galaxies that were later absorbed. Studying these ancient structures helps scientists understand the earliest stages of galaxy formation, a process that began less than 1 billion years after the Big Bang. The halo is also home to Andromeda's faintest and most elusive components: its stellar streams. These streams of smaller galaxies that Andromeda captured and disrupted through gravitational interactions. By mapping the distribution of these streams, astronomers can reconstruct the galaxy's merger history, revealing a timeline of interactions that shaped its current structure. These streams are not static, they evolve over time, mixing with Andromeda and contributing to its overall mass. Andromeda's dark matter halo, though invisible, is one of its most significant features. This vast, diffuse structure extends far beyond the visible galaxy, accounting for most of its mass. The dark matter stars and gas would not remain bound, and its spiral structure would not persist. The presence of dark matter is inferred from the galaxy's rotation, which remains flat even at great distances from the center. This behavior is in the amount of visible matter alone to the dominance of an unseen component. The nature of dark matter remains one of the greatest mysteries in physics. Observing Andromeda's halo offers a unique to study this enigmatic substance, as its proximity allows for detailed measurements of its gravitational effects. By combining data from Andromeda with observations of other galaxies and galaxy clusters, scientists hope to constrain the properties of matter and in shaping the universe. Andromeda's relationship with its satellite galaxies adds another layer of complexity to its story. Smaller systems, numbering more than Andromeda within its dark matter halo. Some, like M32 and M110, are easily visible, are faint and difficult to detect. These satellites are subject to tidal forces that can strip away their stars and gas, Andromeda's mass and forming tidal streams. The ongoing interactions between Andromeda and its satellites prime example galaxy formation, a process that has occurred throughout the universe. The impending collision between Andromeda and the Milky Way will mark a transformative event in the local group of galaxies. This merger, set to occur in about 4.5 billion years, will create a new, massive galaxy that combines the stars, gas, and dark matter of both systems. Simulations of this event predict a dramatic reshaping of both galaxies, with structures destroyed and a spheroidal configuration. This process will also redistribute their dark matter halos, creating a new gravitational equilibrium. During the collision, gas clouds from both galaxies will collide and compress, triggering bursts of star formation. These events, bursts, will illuminate the newly forming galaxy, creating regions of intense brightness. At the same time, the supermassive black holes Andromeda and the Milky Way may merge, releasing enormous amounts of energy in the form of gravitational waves. These waves, ripples in spacetime, outward, carrying information about the black hole's masses and spin. While the Andromeda Milky Way is between stars mean that direct stellar collisions are unlikely. Instead, the merger will reshape the orbits of stars and gas, creating new tidal structures and redistributing material throughout the galaxy. Over billions of years, the two galaxies will settle into a stable configuration, forming an elliptical galaxy that astronomers have dubbed Milkomeda. The study of Andromeda extends across the magnetic spectrum, with ultraviolet, infrared, and X-ray wavelengths, providing a more complete picture of its structure. Ultraviolet light reveals the hottest stars in the galaxy, while infrared observations penetrate dust clouds to uncover regions of active star formation. X-ray emissions, on the highlight high-energy processes near Andromeda's supermassive black hole and within its population of neutrons and stellar mass black holes. The wealth of data collected from Andromeda has implications far beyond the local group. By studying its structure, dynamics, and composition, astronomers can test theories of galaxy formation and evolution that apply across the universe. Andromeda serves as a laboratory for understanding the processes that govern galaxies at all scales, from the smallest dwarfs to the largest clusters. The Andromeda galaxy's vastness embodies the interconnected nature of the universe. Each of its components, from the stars in its disk to the halo, plays a role in shaping its structure and behavior. As our understanding of Andromeda deepens, so too does our appreciation for the forces that govern the cosmos. It stands as a reminder of the universe's boundless potential for discovery, a cosmic neighbor whose secrets continue to inspire and challenge the universe. The Andromeda Galaxy is not merely a subject of awe-inspiring beauty, it is a cornerstone of astrophysical research, so close that it offers a detailed view into processes that govern the universe at large. With every new generation of instruments and theoretical models, Andromeda becomes an even more potent laboratory for exploring the physics of galaxies, the nature of dark matter, and the history of the cosmos. Significant aspect research into Andromeda rotational dynamics. The galaxy's rotation curve, a plot showing how the orbital velocity of stars changes with distance from the center, provides one of the most compelling pieces of evidence for the existence of dark matter. Would be visible matter. The rotation curve of Andromeda remains nearly flat at large distances from its core, even where the visible mass indicates the presence of an unseen halo of dark matter extending far beyond the luminous disk. By comparing the rotation curves of Andromeda with those of other galaxies, astronomers can refine models of dark matter distribution and its influence on galactic structure. In addition to dark matter, studies of Andromeda's stellar populations are unlocking secret formation and evolution. Detailed spectroscopic surveys, such as those conducted with the Keck Observatory Space Telescope, have allowed scientists to determine the metallicity of stars in different regions of the galaxy. Metallicity, the proportion than hydrogen and helium, acts as a cosmic clock, revealing the star formation history of the galaxy. The high metallicity of stars in Andromeda's central bulge reflects a period of rapid star formation, likely driven by the inflow of gas and the intense gravitational core. The outer disk and halo contain stars with lower metallicities, indicating slower chemical enrichment over time. These metallicity gradients are critical for understanding not only Andromeda but also galaxy evolution on a universal scale. For instance, the presence of stars in Andromeda suggests that these stars are remnants of smaller galaxies that merged with Andromeda in the past. Supports the hierarchical galaxy formation. Large galaxies grow through the accretion of smaller ones. By studying the ages and motions of these stars, can reconstruct the timeline of Andromeda's mergers and interactions, painting a picture of its growth over billions of years. One of the most discoveries in recent years has been the identification of tidal streams in Andromeda's halo. These faint structures are the remnants of dwarf galaxies torn apart by Andromeda's hole. Among the most prominent is the giant stellar stream, a structure 100,000 light-years, thought to be the remains of a galaxy that collided with Andromeda about 2 billion years ago. By mapping these streams with hyperments, such as the Gaia story, scientists can probe the gravitational potential of Andromeda's halo, providing insights into the distribution of and the galaxy's dynamic history. Beyond its stars and dark matter, Andromeda's interstellar medium, ISM, is a subject of intense. The ISM, consisting of gas, dust, and cosmic rays, plays a crucial role in the life cycle of galaxies by serving as the reservoir for star formation. Observations in multiple wavelength radio, infrared, and submillimeter have revealed complex structures within Andromeda's ISM, from dense molecular clouds to diffuse atomic hydrogen regions. These structures are shaped by the interplay of gravitational forces, turbulence, magnetic fields, and feedback from massive stars and supernovae. The role of magnetic fields in shaping Andromeda's ISM is an emerging area of. Using instruments such as the Very Large Array and the Atacama Large Millimeter/Submillimeter Array, astronomers are mapping the galaxy's field structure. These fields influence the motion of charged particles in the ISM, affecting star formation and the dynamics of gas. Understanding the strength and orientation of magnetic fields in Andromeda provides a deeper understanding of how galaxies' formation and structure over time. Andromeda galaxies add another layer of complexity to its ecosystem. With over 20 known satellites, Andromeda serves as a microcosm for studying the dynamics of galaxy groups. Some satellites, like M32, show evidence of tidal stripping, where gravitational interactions with Andromeda have removed stars and gas, leaving behind a compact remnant. Others, like M, are actively interacting with Andromeda, contributing material to its halo. These interactions provide a living example of galaxy evolution in action, a detailed view of processes that occur in the universe. The future merger between Andromeda and the Milky Way is one of the most anticipated cosmic events in the local universe. Current simulations of this event, such as those conducted with supercomputers using the Illustris and Eagle cosmological models, predict a series of dramatic transformations. As the galaxies approach, their gravitational interactions will distort their shape in tidages of stars. These features, reminiscent of structures seen in interacting galaxies like the antennae galaxies, provide a preview of what might unfold. The collision will ignite bursts of star formation, driven by the compression of gas as the galaxies merge. In time, their central black holes will coalesce, emitting gravitational waves detectable by next-generation observatories such as the Laser Interferometer Antenna, LISA. Even as we anticipate the future, Andromeda remains a critical subject for understanding galaxy clusters beyond the local group. Its role as the largest member of our local group offers a scaled-down model of the processes occurring in massive galaxy clusters, where interact dark matter halos, gas dynamics, and star formation on a grander scale. By studying Andromeda, scientists refine the truths that apply to systems years away. Andromeda's study is also pushing the boundaries of exoplanet science. Planets in another galaxy challenge, gravitational microlensing and spectroscopy hold promise for identifying planets within Andromeda. Detecting such planets would open a new frontier in the search for extraterrestrial life, providing the first opportunity to study worlds beyond the Milky Way. If Andromeda's planetary systems of the Milky Way, it is with diverse planets, some potentially orbiting within habitable zones where conditions might support life. Telescopes come online, including the extremely large telescope and the James Webb Space Telescope. Andromeda's secrets will continue to be unveiled. These instruments will provide unparalleled resolution and sensitivity, allowing astronomers to study individual stars and planets within, as well as tidal streams and most diffuse dark matter structures. Andromeda, as a living archive of light, will remain a focal point for unraveling the universe's grandest mysteries, inspiring generations of researchers and dreamers alike. The Andromeda Galaxy, as a living archive of cosmic evolution, continues to captivate the scientific community. With its immense size and proximity, it serves as an unparalleled laboratory for testing theories of galactic dynamics, star formation, and the nature of dark matter. As observational tool, researchers increasingly intricate about the processes that shape this massive spiral galaxy and its surrounding environment. One of the areas of research focuses on the interplay between interstellar medium (ISM) and star formation. The ISM is not a uniform structure. It consists of diverse phases, from cold molecular clouds to hot, ionized regions. Molecular clouds, composed primarily of molecular hydrogen, H2, are the birthplace of stars. Observations using radio telescopes like the Atacama Large Millimeter/Submarine, ALMA, reveal these in extraordinary detail. By studying their composition, density, and temperature, scientists gain insights into the conditions that lead to star formation. In Andromeda, these clouds are predominantly located along its spiral arms. Compression of gas by density waves provides the necessary triggers for gravitational collapse. The role of feedback mechanisms in regulating star formation is another critical aspect of Andromeda's. Massive stars, once formed, exert powerful feedback on their surroundings through stellar winds, radiation, and supernova explosions. These feedback processes inject energy into the ISM, heating it and dispersing gas, which can either suppress or stimulate further star formation. In Andromeda, bubbles and shells of iron are visible throughout its disk, offering a dynamical nature of star formation. Andromeda's spiral arms, while appearing as fixed features, are in constant motion. And sustained by density waves, which propagate through the galactic disk, concentrating stars and gas into resemble a spiral. Are not made of physical material but are rather regions of higher gravitational density that travel through the galaxy. Observing these arms in Andromeda has helped refine our understanding of how such structures form and persist in spiral galaxies across the universe. Distribution mass within these arms also provides clues about the interplay between galactic rotation, gravity, and star formation. The central bulge of Andromeda presents a stark contrast to its active spiral arms. This region, dominated by older, redder stars, is relatively quiescent, with little ongoing star formation. The stars in the bulge orbit in complex patterns, influenced by the galaxy's supermassive hole and the dense gravitation of the central region. By studying the motion of these stars using spectroscopy, astronomers can map the distribution of matter, including the unseen mass of the black hole and dark matter. These studies reveal that Andromeda's supermassive, with a mass of 140 million, is significantly larger than the one at the center of the Milky Way, suggesting differences in the growth histories of the two galaxies. The double nucleus of Andromeda, a rare and fascinating feature, continues to be a subject of intense investigation. Detailed observations suggest that it may result of a smaller galaxy, whose core became embedded in Andromeda's central region. This scenario is supported by the presence of distinct stellar populations within the double nucleus, indicating different origins. This finding highlights the dynamic and often violent history of galaxies and mergers that have shaped Andromeda into its current form. Andromeda's extensive halo, stretched beyond its visible disk, area rich with scientific information. This halo contains a mix of stars, globular clusters, and streams of past mergers. Observations using the Hubble telescope have revealed that Andromeda's halo is significantly more massive and extended than previous provided about. The halo also contains metal pores, some of the oldest in the galaxy, remnants phases of galactic formation. These stars serve as fossils, preserving information about the conditions in the universe when Andromeda was just beginning to form. The seas of Andromeda, including M32, M110, and dozens of smaller dwarf galaxies, dynamic and Some of these satellites are in the process of being disrupted by Andromeda's tidal forces, adding to the streams of stars. Others are stable, orbiting at distances where tidal forces are weaker. These satellites provide a studying the hierarchical formation of, showing how smaller systems are absorbed by larger ones over time. They also serve as laboratories for understanding the role of dark matter in shaping the dynamics of small galaxies, as their visible mass is often insufficient to account for their observed collision between and Milky Way, while billions of years in the future, continues to be a focal point of theoretical studies and simulations. By modeling this event using computers, astronomers can predict the stages of the merger, from the initial gravitational interactions to the eventual formation of a single elliptical galaxy. These simulations incorporate data about the mass, composition, and motion of both galaxies, as matter halos, to create highly detailed. The results provide insights into the future of our local into the process of galaxy evolution. In addition to its relevance for understanding large-scale cosmic structures, Andromeda is becoming a target of exoplanetary systems. While direct detection of exoplanets in Andromeda remains beyond planetary formation suggests stars are likely to host planets. Observations of star-forming regions in Andromeda reveal similar to those in the Milky Way, where planets are round stars of various types. Future advancements in observational techniques, such as high-resolution SPI and microlensing, may allow astronomers to detect exoplanets within Andromeda, opening a new frontier in habitable worlds. His role as the largest galaxy in the local group also provides a unique perspective on the dynamics of galaxy clusters. Its interactions with the Milky Way and other members of the local group offer a scaled-down model of the processes that occur in much larger galaxy clusters, where gravitational forces and collisions dominate. By studying Andromeda, astronomers can test theories of cluster evolution, including the influence on the expanse. Every aspect of Andromeda, from its smallest star-forming regions to its vast dark matter halo, contributes to our understanding of the universe. It is not merely a distant object in the sky but a dynamic, evolving system that embodies the processes shaping galaxies everywhere. As technology advances and observational techniques improve, Andromeda will continue to serve as a cornerstone of research, discoveries, and expanding our cosmos. The Andromeda galaxy continues to captivate not only astronomers but a cosmic marvel. Beyond its already well-documented features, there are even deeper questions about its nature. One particularly fascinating aspect is discoveries within its vicinity. These faint, ghostly systems, scattered around Andromeda, low in luminosity to their size. UDGs challenge our understanding of galaxy formation, as they are thought to contain large amounts of having very few stars. Their existence raises questions about how galaxies form and survive in such extreme conditions. Observing these faint galaxies around Andromeda helps astronomers test models of dark matter and study how gravitational interactions with larger systems affect small, diffuse galaxies. Another intriguing topic is Andromeda's stellar remnants, white dwarfs, neutron stars, and black holes. These are essential for understanding the life cycles of stars in Andromeda. By observing the X-rays emitted by binary where a neutron star or accretes material from a companion star, astronomers can measure the mass, spin, and other properties of the remnants. Observations also about the population of high-mass stars that existed in Andromeda's past, as these stars evolve into compact objects. The search for intermediate-mass black holes, IMBHs, within Andromeda is an area of growth. IMBHs are thought to represent a link in the black hole population, bridging the gap between stellar mass black holes and supermassive. Evidence of objects could come from dense in Andromeda's halo or from X-ray sources that exhibit these. IMBHs could help supermassive black holes like the one at Andromeda's center grow over time. The outer edges of Andromeda's disk and also hold surprises, such as extended UV disks discovered by the Galaxy Evolution Explorer, GALEX. UV is the invisible disk of the galaxy. Such discoveries challenge traditional notions of where and how occurs in spiral galaxies, hinting at density gas reservoirs that may slowly contribute to the galaxy's growth over billions of years. A lesser discussed yet intriguing Andromeda is its magnetic field. Magnetic fields are notoriously difficult to study, critical in the behavior of galaxies, sensing the motion of charged particles and the dynamics of the interstellar medium. Recent observations suggest magnetic field is well ordered across its spiral arms and potentially contributing to the formation of dense molecular clouds. By mapping field, scientists uncover regulating star formation flow of gas within the galaxy. In the realm of theoretical physics, Andromeda also provides a unique opportunity for alternative theories of gravity. The behavior of halo, for instance, can be used to test modified Newtonian dynamics, MOND, or other theories that aim to explain galactic rotation curves without invoking matter. Matter remain the accepted explanation. Galaxies like Andromeda critical testing grounds models, ensuring that our understanding of fundamental physics remains robust and open to new ideas. Andromeda's role extends to its positional group, which itself is of the larger cosmic web. The local group is dominated by Andromeda and the Milky Way, but it also includes galaxies like the galaxy M33 dwarfs. By studying the motion of these galaxies relative to Andromeda, astronomers gain insights into the gravitational interactions within galaxy groups. These in turn, distribution of dark matter on larger scales, helping to constrain cosmological models that describe the evolution of the universe from the present day. On a more speculative note, this potential for hosting habitable environments is a topic that sparks the imagination. While exoplanet research within the Milky Way has revealed thousands of studies to open new frontiers. Advanced methods, such as transit photometry or gravitational microlensing intergalactic scale, may allow the detection of stars in Andromeda. If found, their diversity could provide a broader context for understanding the conditions necessary for life. Furthermore, the theory of biochemical markers the presence of life on planets in Andromeda would redefine humanity's place in the cosmos. The exploration is also fueling advancements. Instruments resolving individual stars such as those aboard the Hubble Space Telescope or the upcoming Extreme ELT boundaries of similar computational to simulate the future collision between Andromeda and the Milky Way drives innovation in numerical modeling and high-performance computing. These technologies not only understanding of Andromeda, but also have broader applications in fields ranging from artificial intelligence to climate. As Andromeda grows, appreciation of its role as a cornerstone of modern astrophysics. It is a galaxy that embodies the complexity and interconnectedness. Each new discovery, whether it is the behavior of stars, the distribution of dark matter, or the interactions of satellite galaxies, adds to our understanding of the cosmos and our place within it. Andromeda stands as a symbol of the relentless pursuit of humanity's exploration of the universe. The Andromeda galaxy, vast and enigmatic, represents a known and the unknown, the observable histories that lie beyond. It provides humanity with an unparalleled opportunity to study a galaxy in extraordinary detail, both a mirror and a demanding galaxy's cosmos. Each tidal stream, trace of dark matter within Andromeda tells a story, not just of its own formation, but of the fundamentals that govern the universe. As we probe Andromeda's secrets, we are reminded of the immense scale of the cosmos and our relatively small yet significant place within it. This galaxy, with its trillions of dynamics, to think not only about that shape galaxies, the nature of existence itself. Its eventual collision, an event of unimaginable scale, emphasizes the ever-changing nature of the universe, where no exists in isolation. Andromeda is more than a neighbor, cosmic partner in our journey of discovery. As our technology advances and our curiosity deepens, this majestic continued not only worry but a sense of wonder. Andromeda, we glimpse the infinite possibilities of the cosmos, and in that glimpse, we find both questions to pursuers that redefining of the universe. As a testament to the unending dance of matter, energy, and time, a galaxy that invites us to explore, imagine, and reach beyond.
IC 1101, a colossal elliptical galaxy in the Virgo constellation, ranks among the largest known in the universe. Its immense diameter exceeds 6 million light-years, dwarfing the Milky Way, which spans approximately 1,000 light-years, located at the core of the Abell 2029 galaxy cluster. This cosmic behemoth stands to its index. At its center lies a supermassive black hole, estimated billion solar masses, exerting a profound influence on its structure and the surrounding cosmic environment. This titan of the cosmos is classified as a cannibal galaxy, having merged with numerous smaller systems over billions of years. These relentless mergers have shaped its elliptical and led to the near cessation. Most of its stellar population is over 10 billion years old. System a distinct yellowish hue. The absence of cold gas prevents new stars from forming, while its hot ionized material emits X-rays detectable by space observatories such as Chandra and XMM Newton. The massive halo surrounding this galactic colossus extends well beyond its visible boundaries, composed of stars, gas. It also contains intracluster light, a faint stars ejected during past collisions. These remnants serve as a testament to interactions that have shaped this celestial leviathan over cosmic time, ensuring its continued evolution within the vast Abell 2029 cluster. The study of this stellar giant imparts powerful insights into the formation and evolution of galaxies on a grand scale. As one of the most massive and luminous systems in the observable universe, it challenges our understanding of galactic growth. The role of environment, dark matter, and supermassive black holes in shaping such extraordinary structures remains a central focus of contemporary astrophysics. To as the titan of galaxies, this ancient behemoth continues to inspire awe, prompting further exploration into the mysteries of the cosmos. Situated in the dense environment of the Abell 2029 cluster, this colossal system serves as a natural laboratory for studying the interplay between galaxies and their surroundings. The cluster's intracluster medium, a hot, X-ray emitting plasma, interacts with the giant elliptical, influencing its evolution and that of its satellite galaxies. Gas stripped from smaller neighbors through ram pressure interactions enriches the medium, contributing to the overall complexity of the system. These processes highlight the dynamic nature of galaxy clusters, where gravitational forces and high-energy phenomena shape the universe on vast scales, beyond its scientific significance. This cosmic monarch serves as a reminder of the diversity and scale of the universe. Its immense size, brilliance, and central location within the Abell 2029 cluster make it a prominent cosmic landmark, a beacon of light visible across hundreds of millions of light years. Observing this galaxy provides a glimpse into the distant past, offering insights into the intricate interplay of forces that have shaped the cosmos. As research progresses, this ancient colossus and its analogues will to our quest for understanding the universe offering a window into its boundless possibilities. The giant elliptical of Abell 2029 continues to intrigue astronomers with its sheer scale and complex history. This celestial titan, alternatively called the Abell 20 galaxy, stands as a testament to the immense forces at play in the universe. Measuring over 6 million light-years across, it dominates its galactic cluster in both size and influence, earning titles such as the Colossus of Virgo in astronomical discussions. This supergiant has undergone countless mergers, consuming smaller galaxies in a process that has shaped its current structure. Each interaction has added stars and gas, further enriching the galactic core. This relentless process, known as galactic cannibalism, underscores the dynamics within dense cosmic environments. At its heart lies a supermassive black hole of extraordinary proportions, sometimes referred to as the gravitational anchor of Abell 2029. With a mass surpassing 40 billion suns, it is among the largest ever detected, governing the motions of stars in the galaxy, while exerting influence on the broader cluster environment. The intense gravitational field of this singularity contributes to the galaxy's luminous core, radiating across vast distances, earning it epithets such as the light beacon of Virgo. The stellar population of this ancient colossus is predominantly old and yellowish, characteristic of elliptical galaxies. Most stars within this vast system exceed 10 billion years in age, marking a galaxy that has long since exhausted its supply of cold gas necessary for star formation. Instead, the stellar graveyard of Abell 2029 glows faintly with a golden hue, a visual indicator of its advanced evolutionary stage. Surrounding this interstellar monarch is a vast halo of dark matter and interstellar material, often termed the cosmic veil of Abell 2029, extending far beyond its visible boundaries. This halo influences the cluster's gravitational dynamics. Within it, intra-cluster light, a faint glow from stars stripped from their original galaxies, adds an ethereal quality to the region. These orphan stars, drifting through the intergalactic sea, serve as evidence of the violent history of galactic interactions that have defined the Abell 2029 monarch. The surrounding environment of this galactic elder is rich with X-ray emissions, a consequence of the hot plasma filling the Abell 2029 cluster. These high-energy phenomena, observable by Chandra and XMM Newton, reveal the turbulent conditions within the X-ray furnace of this dense system. Interactions with the cluster's tidal forces strip gas from smaller galaxies, enriching the intra-cluster medium and fueling the ongoing evolution of this cosmic giant. Studying this luminous elder of the universe provides unparalleled insights into galaxy formation and evolution. As one of the largest known galactic structures, it serves as a crucial subject for exploring extreme cosmic phenomena. The role of supermassive black holes, dark matter, and galactic mergers in shaping such immense systems remains a fundamental question in astrophysics, with the Colossus of Abell 2029 offering valuable clues, despite its age and apparent dormancy in star formation. This golden leviathan continues to exert significant influence on its surroundings. Its gravitational pull dictates the of satellite galaxies and contributes to the broader dynamics of the Abell 2029 cluster. as the gravitational heart of Virgo exemplifies the scale and power of cosmic structures, a reminder of the vast forces governing the universe. This eternal sentinel of the Virgo supercluster, referred to as the cosmic giant, stands as a silent witness to nearly the entire history of the universe, with an unfathomable size. This ancient behemoth has absorbed and consumed countless smaller galaxies, preserving a vast record of cosmic evolution. Within its structure, dot at its core, lies a supermassive black hole of unimaginable scale, often described as the abyssal king or the dark heart of Abell 2029. With a mass exceeding 40 billion suns, its gravitational pull is so intense that even light struggles to escape. The energy released by matter spiraling into this behemoth generates a luminous halo of X-rays, and that signals its presence across intergalactic space. This singularity, the cosmic anchor, dictates the structure of its host galaxy, binding stars and dark matter in an unending gravitational dance. The luminous behemoth stands as a monument to galactic cannibalism, a relentless cosmic predator. Over billions of years, it has consumed not just a few, but potentially thousands of smaller galaxies, merging their stars, gas, and dark matter into its sprawling form. These ancient collisions, some violent and others gradual, have left imprints across its vast halo, a graveyard of shattered galactic identities. Each merger has been a step toward its immense scale, making it one of the largest galaxies ever observed. Often described as the universal apex, it represents the ultimate fate of many evolving galaxies. Despite its outward stillness, this silent monarch is far from dormant. While its visible light radiates a golden hue, a testament to its aging stellar population, its hidden layers remain active. X-ray telescopes reveal a sea of hot plasma permeating the intracluster medium, a cauldron of gas stripped from neighboring galaxies via gravitational interactions. This invisible fire glows in hikes, exposing the turbulent forces shaping the Abell 2029 cluster. The galaxy's cosmic shroud, an immense halo extending beyond its core, envelops countless orphan stars. These unbound celestial wanderers drift aimlessly through the cluster, therefore known as intracluster light, preserving the story of ancient galactic violence and ongoing cosmic evolution. Here, in the interplay of light and shadow, lie countless mergers, some unfolding over millions of years, others in cataclysmic bursts. Yet, it is not only its scale that makes this stellar colossus, but it challenges fundamental understandings of the universe itself. How did such a massive structure form? What are the limits of galactic growth? These unanswered questions push astronomers to look deeper into the void, searching for clues within the glow of this cosmic elder. Its existence reminder that, despite its apparent stillness, the universe is an ever-evolving place of energy, motion, and transformation. The role of dark matter in shaping this cosmic sovereign cannot be overstated. Without this enigmatic, unseen force, its vast mass would not remain intact. Scientists theorize that this dark empire of the cosmos is encased in a titanic dark matter halo, stretching far beyond its luminous boundaries. This invisible structure its stars together, but also dictates the motion of galaxies within the Abell 2029 cluster. Studying dark matter in such a monumental system provides essential insights into the forces that govern the universe on the largest scales. Perhaps most hauntingly, this eternal giant offers a glimpse into the ultimate fate of galaxies like our own. Over billions of years, as galaxies collide and merge, they gradually lose their distinct forms, their spirals fading into smooth, featureless ellipses filled with aging stars. In this way, as a harbinger of inevitability, offering a vision of what the Milky Way and its neighbors may one day become. Yet, despite its dominance, even this galactic juggernaut is not eternal. The universe's expansion will eventually isolate it, as neighboring galaxies recede beyond the observable horizon. Trapped in an ever-growing void, this universal chaos will gradually dim, its stars burning out, leaving behind a cold, dark remnant. But for now, it remains a beacon of knowledge, a living relic of the universe's tumultuous past, the ancient monarch of Abell 2029. One of the grandest elliptical galaxies ever discovered, is more than a single entity. It is a microcosm of cosmic history. Every star within its vast expanse, every faint whisper of gas, every drifting shadow of dark matter holds a story spanning billions of years. This stellar labyrinth challenges our perceptions of time and space, inviting us to unravel its secrets, while reminding us of the universe's boundless complexity. The sheer magnitude of this galactic behemoth, sometimes called the infinite tapestry of Virgo, places it in a class of its own. Spanning over 6 million light-years in diameter, it could only have formed in one of the densest and oldest galactic environments. The Abell 2029 cluster, a gravitational cauldron housing thousands of galaxies, provided the ideal conditions for such a titan to emerge, often referred to as the cosmic overlord. This dominant force at the cluster's core sculpts the motions of stars, gas, and galaxies across millions of light-years. At its center lies its most mysterious and formidable feature, a supermassive black hole of scale, sometimes called the cosmic abyss. Leviathan is not merely a point of intense mass, it is a dynamic engine, consuming matter and unleashing vast amounts of energy through radiation and relativistic jets. These jets, stretching for hundreds of thousands of light-years, act as cosmic lighthouses visible at their surrounding environment, heating nearby gas and preventing it from stars. The intricate relationship between this dark heart and its host galaxy is one of the many puzzles astronomers seek to unravel. The Virgo Colossus, with its ancient history and staggering scale, continues to intrigue scientists, offering a glimpse into the most extreme conditions the cosmos can produce. Every observation of this celestial titan deepens our understanding of the vast and evolving universe, reinforcing its place as one of the greatest galactic wonders ever discovered. This galaxy, sometimes poetically called the eternal jewel of the universe, stands as a relic of a bygone era, a testament to the cycle of galactic life and death across cosmic timescales. Its stars, predominantly ancient, resemble the dim embers of once bright stellar populations, collectively known as the Golden Veil of Abell 2029. These aging stars give the system its characteristic yellowish hue. The absence of young, blue stars confirms that star formation within this stellar mausoleum ceased long ago, leaving behind a tranquil but enduring celestial giant. Yet, for all its apparent serenity, this universal titan bears visible scars of its violent past. Faint trails of drifting remnants of past galactic collisions surround it like ghostly echoes of long-lost galaxies. These orphan stars, stripped from their original homes, now drift aimlessly in the gravitational tides of the cluster. Observing this cosmic haze allows astronomers to reconstruct the history of mergers that have fed this stellar behemoth over billions of years. Each sense more than just a lost galaxy, long since absorbed into the greater whole. The surrounding environment, often called the fiery realm of Abell 2029, is a place of extreme conditions. The intracluster medium, a searing plasma heated to tens of degrees, fills the space. This inferno is a direct result of gravitational energy released during galactic interactions. As smaller systems are drawn into the gravitational throne of the cluster's core, their gas is stripped away, enriched medium. These processes shape not only the cluster's fate, but also the continued evolution of this cosmic monarch. The story of this interstellar giant unfolds across the entire electromagnetic spectrum. Radio waves reveal vast lobes of relativistic particles, remnants of past outbursts from its central black hole. Infrared surveys uncover traces of dust-silent echoes of an era when star formation was still possible. Every wavelength of light paints offering astronomers a multifaceted view of the infinite expanse of Abell 2029. Yet, the greatest mystery of this silent king of clusters lies in what cannot be seen. Dark matter, the invisible substance that dominates the universe's mass, plays a fundamental role in its structure. Without an immense dark matter halo encasing this stellar leviathan, its gravitational influence could not hold such a sprawling structure. Together, this invisible crown extends well beyond the galaxy's visible boundaries, binding not only its stars, but also anchoring the entire Abell 2029 cluster. The timeless Colossus is more than just a relic. It is a symbol of the universe's relentless expansion. As space itself stretches, galaxies grow more isolated. One day, far in the future, the Abell 2029 cluster will drift so far from its cosmic neighbors that it will become an island of light in an otherwise unreachable void. The stellar empire will remain, but its surroundings will fade into darkness, a sobering reminder of the inexorable forces shaping the cosmos. Yet, in its present form, the eternal beacon of Virgo continues to shine, offering humanity a glimpse into the ultimate limits of galactic evolution. It stands as both a challenge and an inspiration, a cosmic enigma urging astronomers to push the boundaries of knowledge. Each discovery brings us closer to unraveling the mysteries of this cosmic colossus, deepening our understanding of the largest and most ancient structures in the universe. The primordial primordial sovereign of Abel 2029, sometimes called the cosmic monarch of Virgo, is not merely a passive, it is a living record of the universe's history. Every star in its vast expanse, every whisper of gas, and every drifting shadow of dark matter tells a story spanning billions of years. This stellar labyrinth challenges our perceptions of time and space, inviting us to decipher its secrets and reminding us of the infinite complexity of the cosmos. The sheer size of this galactic behemoth, sometimes described as the infinite tapestry of Virgo, places it in a category of its own. Spanning over 6 million light-years, it exists only in the densest and most ancient galactic environments. The Abell 2029 cluster, a gravitational cauldron of thousands of galaxies, provided the perfect conditions for such a titan to emerge. At the heart of this vast system, the cosmic overlord dominates its region, its gravity shaping the motions of galaxies, stars, and gas across an immense scale. For all its grandeur, this celestial titan is not an immortal entity. One day, its stars will fade, its black hole will quiet, and its surroundings will slip beyond the cosmic horizon. But for now, it remains a beacon of knowledge, a monument to the forces that have sculpted the universe. Studying this stellar leviathan continues to challenge and refine our understanding of how galaxies live, evolve, and ultimately face their cosmic fate. The environment of the celestial monarch is one of extremes. The Abell 2029 cluster, a dense conglomeration of galaxies, is suffused with hot plasma that radiates X-rays detectable by telescopes like Chandra. This cosmic furnace is fueled by gas stripped from smaller galaxies as they pass through the cluster, compressed and heated by gravitational forces. These interactions cluster medium, creating the high-energy conditions necessary for sustained X-ray emissions. For now, this timeless sentinel stands as a reminder of cosmic grandeur, a testament to the past, a guide to the present, and a vision of the universe's inevitable fate. Despite its eventual fate, the universal titan remains a source of inspiration and discovery, changing our understanding of the cosmos. Each new observation brings us closer to uncovering not only the nature of this galactic giant, but also the fundamental forces that shape the universe itself. The primordial Colossus, sometimes revered as the king of galactic giants, stands as a monument to the immense creative and destructive forces at play in the cosmos. Story, spanning billions of years, is a narrative of formation, destruction, and rebirth, a microcosm of the universe's constant flux. This galactic juggernaut embodies both the beauty and the violence of large-scale cosmic evolution, offering an unprecedented for exploring the mechanics of the universe. At its heart lies a region of unfathomable energy and density, a supermassive black hole, often referred to as the engine of eternity. This gravitational leviathan does more than consume, it transforms. Gas and dust drawn into its event horizon are either devoured or ejected in powerful relativistic jets, traveling near the speed of light. These outflows heat surrounding gas, preventing new stars from forming and shaping the broader structure of the galaxy. This dark monarch at the galaxy's core is both a creator and a destroyer, continuously influencing the evolution of its host. Moving outward from this gravitational abyss, the structure of the galaxy itself stands as a testament to endurance, sometimes romantically termed the stellar palace. It houses trillions of stars, many of which have long outlived their prime. These ancient suns, dimmed and reddened by time, are relics of a distant epoch when the galaxy teemed with star-forming activity. Today, their soft radiance gives the celestial elder its characteristic golden hue, a reminder of its advanced stage of evolution. Beyond this warm glow, an even more elusive component, dark matter, the silent architect of the cosmos. This unseen force envelops the galaxy, providing the gravitational cohesion necessary to maintain its vast structure. The dark halo surrounding the stellar Leviathan extends millions of light-years beyond its luminous core, not only holding the galaxy together, but also influencing the entire Abell 2029 cluster. The cluster itself, sometimes described as the arena of giants, is a battlefield of cosmic interactions. Smaller galaxies, drawn toward the universal colossus, spiral into its gravitational grip, stripped of their gas and stars before being absorbed. The remnants of these encounters are scattered throughout the cluster in the form of intracluster light, faint glimmers of stars torn from their original homes. This ghostly veil of Abell 2029 tells a silent story of galactic cannibalism, marking the violent history that has fueled the growth of this enormous system. Adding another layer of intrigue to this environment is the superheated plasma that fills the cluster's vast expanse. This cosmic furnace glows brilliantly in X-rays, revealing the turbulent processes that have shaped 29 over billions of years. Galactic collisions and mergers continuously churn this high-energy medium, keeping it at extreme temperatures. Paradoxically, this plasma, while binding the cluster together, also signals the end of star formation by preventing gas from cooling enough to condense into new stars. This delicate balance of creation and destruction defines the ecosystem of the stellar sovereign. As astrophysicists continue to probe the depths of this cosmic giant, its mysteries deepen. Each layer of its structure tells a different part of the story. The gravitational heart pulsing at its core, the ancient stellar palace glowing in quiet grandeur, the vast dark halo dictating its stability, and the luminous trails of lost stars drifting in the cluster's gravitational sea. These interwoven elements remind us even the most massive structures in the universe are shaped by an intricate dance of forces stretching across billions of years. Ultimately, this celestial titan stands as one of the greatest testaments to the universe's power, complexity, and endless potential. Will one day fade into the growing void of an ever-expanding cosmos. Legacy will provides explorations into the nature of galaxies, black holes, and the unseen forces that govern reality itself. As we peer deeper into the stellar abyss of this galactic giant, its past becomes even more compelling. How many galaxies did it consume? Current size? What were the dynamics of those mergers? Astronomers have detected faint tidal streams torn apart by its immense gravitational pull, offering glimpses into its history. Each stream, each ripple of starlight, is a chapter in a saga of cosmic dominance, written over eons. Beyond being a relic of the past, this silence also holds clues about the universe's future. As the cosmos continues to expand, massive ellipticals like this one provide a vision of what may become of galactic clusters in the distant Others, the Milky Way, and its neighbors may merge into a single behemoth, much like this future vision of galactic evolution. This realization lends a personal dimension to the study of this distant Leviathan, linking cosmic home to the broader narrative of time and transformation. Its grand is not over unfathomable. Its stars will exhaust their fuel, fading into remnants, like white dwarfs and neutron stars. The black hole at its core, once a voracious consumer of matter, will eventually fall silent, emitting only the faintest traces of energy. In the fuse of this once will dim into a cold, dark remnant. Inevitable fate is a poignant reminder that even the structures are transient in the grand design of the cosmos. Yet, for now, the stellar emperor shines on, a marvel of cosmic architecture and a testament to the dark matter and time. It remains a focal point of human curiosity, pushing the boundaries of astrophysical reach. More than just a galaxy, it is a monument to cosmic evolution, a beacon of the universe's ability to create both beauty and complexity on unimaginable. The eternal nine, the silent architect of cosmic history, continues to captivate astronomers and philosophers alike. Spanning only light years, this titan of the cosmos stands as a testament to the scale, complexity, and dynamism of the universe, an artifact of ancient mergers, relentless gravitational dominance, and the steady march of. At its core lies one of the most enigmatic forces in existence, a supermassive black hole, often referred to as the abyssal monarch. This immense singularity wields a gravitational influence so profound that it dictates not only the fate of its host galaxy, but also the surrounding cluster. Matter spiraling into this void generates torrents of high-energy emissions, transforming the black hole into a beacon at the heart of a slowly aging structure. Yet, this dark sovereign is more than a consumer, it is a shaper of galaxies. As it devours matter, it releases immense radiation and energy, heating surrounding gas in a process known as feedback. This cosmic paradox, where a black hole both suppresses and sustains galactic growth, plays a crucial role in stabilizing the galactic sovereign, ensuring its continued reign over the Abell 2029 cluster. The stars of this timeless titan, often described as the golden relics of the cosmos, are among the oldest in the universe. Glowing in muted shades of yellow and red, they stand as remnants of a bygone era when the galaxy was young and bursting with stellar birth. Now, the stellar tapestry of this celestial Leviathan is woven from aging giants, their fuel nearly spent, bright light fading into cosmic memory. The lack of cool gas and newborn stars gives the system its signature stillness, a tranquil facade, history of its evolution. Encircling this ancient core is the cosmic shroud of intracluster light, a faint, ghostly glow torn from their original galaxies during past mergers. These drifting cosmic vagabonds serve as spectral reminders of the many galactic bodies that were absorbed into the greater whole. By studying this stellar haze, astronomers can retrace the steps of its violent past, deciphering the collisions and mergers that built this celestial empire. Yet, The true scale of this celestial giant becomes evident when considering its dark matter halo, sometimes referred to as the invisible crown of Abell 2029. This vast, unseen structure extends far beyond its luminous core, providing the gravitational foundation necessary for its immense size and stability. More than just a binding force, this dark foundation dictates the motion of thousands of smaller galaxies within the cluster, shaping their interactions and long-term fates. Unraveling the mysteries of this halo is essential to understanding dark matter, one of the universe's most elusive and fundamental components. The Abell 2029 cluster, often described as the cosmic cauldron, is a theater of galactic interactions. Smaller galaxies, unable to resist the gravitational draw of the universal colossus, spiral toward it, stripped of gas and stars before being consumed. Their remnants linger as dim streams of light, forming what astronomers call the ghostly veil of Abell 2029. This diffuse glow is a silent record of galactic cannibalism, a testament to the relentless cycle of mergers that has shaped this enormous system. Adding to its enigmatic nature is the vast ocean of superheated plasma that permeates the cluster, known as the cosmic furnace. This X-ray bright medium, sustained by the turbulence of galactic collisions, serves as both the glue holding the cluster together and a barrier preventing new star formation. Its intense heat keeps interstellar gas from cooling, ensuring that stellar nurseries remain dormant. This delicate balance of creation and destruction defines the ever-changing fate of this stellar sovereign. As astrophysicists continue to probe the depths of this cosmic giant, its mysteries deepen. Every layer of its structure, the gravitational heart, the ancient stellar palace, the cosmic shroud of lost stars, and the vast dark halo reveals a different piece of the puzzle, each one unlocking more secrets of the universe's grand design. One day, as the universe expands ever outward, this celestial titan will stand alone, a silent witness to the passage of cosmic time. Yet, even in solitude, it will remain a monument to the forces that sculpt the cosmos. Its presence in the sky serves as a challenge, urging humanity to reach further, to question deeper, and to seek the hidden mechanisms of reality. For now, the stellar emperor continues its reign, offering a window into the distant past, while illuminating the pathways that lead toward the future. As long as its light reaches us, it will remind us of our place in the cosmos and the endless wonders that await discovery. The universal sovereign is not merely a component of its cluster, it governs it. Its immense gravitational pull, amplified by its dark matter halo, dictates the motions of surrounding galaxies, shaping the entire Abell 2029 system. This influence extends for millions of light years, making this colossal galaxy more than just a celestial body. It is the central anchor of a vast cosmic ecosystem. The gravitational interactions it drives ensure the cluster's ongoing evolution, fueling its dynamic and ever-changing structure. Observing the stellar colossus is a study in cosmic history and future potential. Often described as a cosmic time capsule, it holds within its vast expanse a record of nearly the entire history of the universe. Every faint stream of intracluster light, every ripple of dark matter, and every ancient star is a fragment of a grand puzzler, silent archive chronicling the transformation of the cosmos from its infancy to the present day. This eternal beacon also offers a glimpse into the distant future. As galaxies within the Abell 2029 cluster continue to merge and evolve, this Leviathan will likely grow even larger, absorbing more matter and further consolidating its dominance over time as the universe expands. This cosmic monarch will become isolated, trapped in an ever-growing void. Trillions of years from now, its stars will fade, leaving behind only remnants, a cold, dark relic of a universe once filled with brilliance. For now, however, this universal titan remains a masterpiece of cosmic engineering, a living testament to the shape of the largest structures in existence. It challenges us to think beyond the limits of human experience, to grasp the vastness of the universe and the mysteries it holds. Insight into this galactic colossus brings us closer to the broader workings of the cosmos. This silent titan of the cosmos, sometimes referred to as the galactic monarch of eternity, looms as an inner fortress whose grandeur surpasses even the wildest imagination. Explorers, endless speculation, stirring curiosity evident within its colossal structure, spanning over years. This stellar Leviathan exists on a scale that defies conventional understanding. To grasp its enormity is to confront the unfathomable. It could engulf thousands of galaxies, the size of the Milky Way. How did this cosmic colossus attain such magnitude? Its origins are rooted in galactic collisions, mergers, and a testament to a universe in perpetual motion. Construction scale dot at its heart. The Abyssal Emperor, a supermassive whole of unimagined, reigns over this galactic dominion, estimated at more than 40 billion times the mass of the Sun. This dark heart influences not only its home, but the entire Abell 2029 cluster. Sometimes called the cosmic maelstrom, this singularity devours matter with insatiable hunger, unleashing violent jets of energy through space like cosmic spears. Yet, it suppresses star formation, ensuring that this ancient is tranquil, undisturbed by the chaos it once fed upon. The galactic core, often described as the Golden Throne, is a dense concentration of ancient stars, their once brilliant light softened by the passage of billions of these stellar relics, clustered tightly in form a radiant hub of golden hues. The absence of young, blue stars in this stellar mausoleum signals the long-dormant era of star formation. Yet, though this galaxy has aged, its influence endures, a silent architect in the grand theatre. Encircling the stellar monarch is its ethereal halo, a region known as the Veil of Lost Galaxies. This vast expanse of faintly glowing light consists of intracluster stars, cosmic orphans stripped from their homes during past mergers. Drifting aimlessly, these remain within the gravitational grasp of the ghostly. The most sensitive, a haunting reminder of the that sculpted this great cosmic entity over billions of years. Yet, the visible components of this galaxy, as immense as they are, tell only part of the story. Encasing the timeless sovereign is a dark matter halo, an unseen force that provides the structural foundation of size. This shadow crown extends far beyond its luminous boundaries, shaping not just its own fate, but that of the entire Abell 2029 cluster. Without this hidden framework, the gravity needed to bind such an immense structure together would not exist. Understanding this dark halo is key to unlocking the deeper mechanics governing the universe. The environment surrounding this eternal colossus is as fascinating as the galaxy itself. The Abell 2029 cluster, sometimes described as the cosmic battleground, is a dense region of space teeming with smaller galaxies, each navigating the gravitational currents of the colossal system. Over billions of years, these galaxies have been drawn toward the cluster's center, stripped of their gas and stars, before becoming part of the expanding mass of the dominant galaxy. This cosmic furnace glows in X-rays, illuminating the ongoing high-energy processes that shape the cluster's structure. The interplay between this stellar overlord and its environment is an active and evolving process. As it continues its reign, smaller galaxies succumb to its gravitational pull, their material merging with the expanding mass of the colossus. This relentless cycle ensures that the galaxy will only grow larger, solidifying its status as the ultimate galactic predator. Yet, paradoxically, even as it consumes, it stabilizes, anchoring the cluster and preventing its galaxies from drifting into the cosmic abyss. Studying this universal titan, the light we observe from this galaxy today is a message from hundreds of millions of years into a past, both distant and or inspired, celestial time and space, connecting the present to the earliest epochs of the universe and offering a glimpse into its eventual fate. Story of this galactic sovereign, the story itself, a saga of relentless expansion, transformation, and survival. It's a reminder of the infinite possibilities lie within the cosmos, allowing us to explore, to question, and to marvel at the mysteries hidden in the depths. The cosmic monarch of eternity, often eternal, ruler of galactic evolution, remains both a scientific enigma and a philosophical wonder. More than just an object of study, this stellar juggernaut of Virgo continues to intrigue those who seek answers about existence and the ultimate verse. This celestial leviathan is not merely a relic of the past, it is a silent storyteller, a relic of creation whispering tales from the dawn of time. The gravitational sovereign, the heart of this immense galaxy, is a force beyond human comprehension. One of the largest supermassive black holes ever detected, it serves as the galaxy's central engine, consuming matter that ventures too close while unleashing immense energy. The X-ray emissions from its accretion disk reveal the staggering temperatures and chaotic forces at play within this cosmic abyss. These are not merely echoes of destruction, they are windows into the deepest laws of the universe, offering astronomers invaluable insights into the nature of space-time, gravity, and energy. Yet, the influence of this dark core extends far beyond its immediate vicinity. The energy released from the black hole radiates outward, heating gas within both the galaxy and the surrounding Abell 2029 cluster. This process, known as active galactic nucleus feedback, prevents the cooling, of gas that would otherwise fuel new star formation. In this way, the cosmic maelstrom shapes the galaxy's future, halting stellar birth while ensuring its continued existence as an ancient, colossal structure. This paradox where destruction sustains longevity lies at the heart of the galaxies. Evolution. As the universe expands, galaxies like this one will drift into isolation, their once thriving clusters stretching into the cosmic abyss. Trillions of years from now, the stars within this behemoth will fade, leaving behind only remnants: white dwarfs, neutron stars, and black holes. The supermassive black hole at its core, once a voracious consumer, will eventually fall silent, emitting only faint whispers of radiation as it slowly evaporates over eons. Yet, for now, this universal titan shines on, its light traversing the vast cosmic expanse, a testament to the forces that shape the grandest structures in existence. It is a monument to cosmic evolution, a beacon of the universe's ability to craft beauty and complexity on unimaginable scales. The stellar cathedral of this galactic colossus is a testament to the vast forces that have shaped it over billions of years. Within its core, some of the oldest stars in existence remain as relics of a time when this galaxy was young, filled with the raw material of creation. Now, these ancient suns cluster together in a dense, golden-hued mass, their light softened by eons of cosmic evolution. Subtle fluctuations in their brightness and motion reveal traces of past mergers, the gravitational echoes of long-lost galaxies now absorbed into this immense structure. Visible expanse, a ghostly veil, stretches into the darkness, a shroud of lost galaxies, composed of stars that were stripped from their original homes during past encounters, no longer tethered to any single system. These celestial wanderers drift through the vastness of the cluster, forming what astronomers call intracluster light. This faint, ethereal glow is more than just a remnant of destruction. It is a silent archive of the violent interactions that have defined this galaxy's relentless expansion. Encasing this behemoth is a dark matter halo, an unseen but all-encompassing scaffold of gravity that extends well beyond its luminous boundaries. Without this invisible framework, the galaxy's immense size would be impossible. Its stars and gas would simply drift apart into the void. This dark foundation not only anchors the galaxy, but also shapes the motion of thousands of smaller galaxies within its cluster. Understanding this vast, hidden component remains one of the greatest challenges in modern astrophysics, as it may hold the key to unraveling the true nature of the cosmos itself. The surrounding cluster is a dynamic battlefield. Are drawn toward the gravitational might of this cosmic predator, stripped of their material, and ultimately consumed. These encounters fuel a superheated sea of plasma, a reservoir of X-ray emitting energy that illuminates the structure of the cluster. This fiery medium, sustained by eons of galactic collisions and black hole act, reveals the turbulent processes that govern the long-term evolution of this region. Stability. This galaxy immutable of light, every displaced star, every trail of cosmic debris whispers of past destruction of smaller galaxies torn apart, their material absorbed, their identities lost within the ever-growing expanse of this celestial leviathan. It is both a relic of the past and a force that continues to shape the fabric of the cosmos itself. As the universe expands, this galactic titan will eventually become an isolated island of light, drifting alone in an increasingly dark and empty void. Over trillions of years, the last of its stars will fade, leaving behind only remnants, white dwarfs, neutron stars, and black holes. Its supermassive black hole, once a ravenous force of gravity, will grow silent, emitting only faint whispers of energy as it slowly decays. For now, though, this celestial monarch endures, its light reaching us across hundreds of millions of light-years, a beacon illuminating the depths of time and space. It stands as a monument to the invisible forces that shape the universe, reminder of the boundless creativity of the cosmos, and a challenge to our understanding of galactic evolution. This timeless titan inspires profound questions. How did the universe come to be? What forces dictate its fate? What role do galaxies like this play in the grander scheme of cosmic history? Every photon of light that reaches us from this immense structure carries the echoes of an ancient past, urging us to look beyond the limits of human understanding, more than just a galaxy. This stellar cluster is a symbol of cosmic entrance, a testament to the grand scale of time, space, and gravitational power. An object of study, but a celestial storyteller, whispering tales of creation, destruction, and the relentless march of time. Beyond its visible structure lies a ghostly veil of intracluster light, a diffuse, ethereal glow from countless stars that were stripped from their parent galaxies and set adrift within the Abell 2029 cluster. These orphan stars, no longer bound to any singular home, drift in the vast sea of gravitational currents, silent witnesses to the cosmic battles of creation and destruction. Their faint light is a whisper of past turmoil, a quiet testament to the violent history of mergers and interactions that sculpted this stellar colossus into the behemoth it is today. Enclosing this empire of stars is its invisible throne, a dark matter halo that defines its true scale and gravitational might. This unseen framework, composed of enigmatic particles yet to be fully understood, is the hidden foundation upon which this galaxy's dominance rests, extending well beyond its luminous core. This massive halo anchors the entire Abell 2029 cluster, influencing the orbits of thousands of smaller galaxies and maintaining the delicate equilibrium of this vast cosmic system. The surrounding cluster, often referred to as furnace, is a realm of high-energy interactions where galaxies collide, evolve, and ultimately succumb to the relentless pull of gravitational forces. At its core, a vast reservoir of superheated plasma glows in X-ray wavelengths, a fiery consequence of the gas stripped from infalling galaxies. This cosmic fire, fueled by the remnants of stellar explosions and galactic collisions, enriches the intracluster medium, forging new elements and reshaping the environment, ending cycle of transformation. Yet, even as it reigns over the cluster, this celestial monarch is not immune to the relentless expansion of the universe. As dark energy accelerates the stretching of spacetime, galaxy clusters will drift ever further apart, their ancient light fading into the abyss. In the distant future, IC 1101 will become an isolated beacon in an empty universe, disconnected from all but the stars trapped within its gravitational embrace. Over trillions of years, its brilliance will wane, its stars will wither into white dwarfs, neutron stars, and black holes, and its once mighty core will grow silent. Even its dark sovereign, the supermassive black hole that once shaped its destiny, will not last forever. Over unimaginable eons, it will slowly evaporate through the quiet process of Hawking radiation, disappearing into the void. The immortal sentinel, once the heart of an empire spanning millions of light years, will fade into a shadow of its former self, a monument to an era long past. Yet, the story of this cosmos is not one of mere decline, but of entrance and transformation. Every collision, every merger, every upheaval that led to its formation is etched into the larger history of the universe itself. The galaxies it consumed, the elements it spread, the stars it nurtured all have played a role in shaping the cosmos. For humanity, IC 1101 is more than an astronomical curiosity. It is a mirror to our own existence. It humbles us, reminding us that our time in the cosmos is but a fleeting moment against the backdrop of eternity. Yet, it also inspires us, driving us to seek, to wonder, to push the limits of our understanding. Its golden glow carries whispers from the past, its massive halo binds together an entire cluster, and its central abyss hints at the deepest mysteries of spacetime itself. As scientists peer ever deeper into its ancient light, they uncover not just the story of a galaxy, but the story of the universe itself. IC 1101, the timeless sovereign of the stars, is more than just a remnant of the past. It is a beacon guiding us toward the future, cosmic pathways we have yet to explore, even as its final fate is sealed. This eternal colossus leaves behind a legacy written in the very fabric of space and time. It reminds us that even the grandest structures are impermanent, that the universe is in a constant state of flux, and that within that impermanence lies an unparalleled beauty that compels us to explore, to question, and to embrace the infinite possibilities of the cosmos. The story of this cosmic titan is not just the story of a galaxy, it is our story as well. In its unfathomable scale and incomprehensible history, we find both awe and belonging. It stands as a testament to the forces that shape existence, to the relentless march of time, and to the delicate balance between creation and destruction, entrance and transformation. And in that realization, we glimpse a fundamental truth. In the vast expanse of space and time, we are all part of something far greater than ourselves.
The Andromeda Galaxy, also known as Messier 31, M31, captivating objects in our universe. Located approximately 2.5 million light years from Earth. It is the closest spiral galaxy to our Milky Way and the largest in our local group of galaxies, which also includes the smaller triangulum galaxy M33. Andromeda's staggering beauty and scientific significance have made it a focal point for astronomers and space enthusiasts alike, serving as a bridge between our cosmic neighborhood and the farthest reaches of the universe. With over a trillion stars, vast clouds of interstellar gas, and dark matter halos extending far beyond its luminous boundaries. Andromeda is not just a galaxy, it's a galactic metropolis. Its immense size, intricate structure, and proximity make it an ideal target for scientific exploration, enabling us to probe the secrets of galaxy formation, evolution, and the ultimate fate of our universe. The Andromeda galaxy is roughly 220,000 light years in diameter, making it more than twice the size of the Milky Way. Its sheer mass, estimated to be around 1.5 trillion solar masses, provide scientists with the natural laboratory to study the interplay between gravity suggest that Andromeda may contain as many as 26 satellite galaxies orbiting its periphery, offering insights into the hierarchical formation of galactic structures. One of Andromeda's most remarkable features is its double nucleus, a peculiarity that hints at a complex history of galactic mergers and interactions. The central region of M31 houses a dense collection of stars surrounding a supermassive black hole, estimated to be 140 million times the mass of our Sun. The presence of this black hole fuels fascinating phenomena, including intense radiation bursts and the accretion of stellar material, shedding light on the dynamics of galactic cores. Unlike the Milky Way, Andromeda's spiral arms are relatively well defined, giving it a classic pinwheel appearance. These arms are teeming with regions of active star formation, where immense clouds of hydrogen gas collapse under their own gravity to form new stars. The galaxy's bright blue clusters, seen in ultraviolet light, are a testament to the ongoing birth of massive, short-lived stars that will eventually explode as supernovae. The older reddish stars in years. These populations provide a glimpse into the early epochs of galactic evolution, helping scientists piece together the history of star formation in our local universe. Perhaps the most tantalizing aspect of the Andromeda galaxy is its impending collision with the Milky Way. Observations reveal that Andromeda is hurtling toward us at a speed of about 110 kilometers per second. In approximately 4.5 billion years, the two galaxies are expected to merge in a spectacular cosmic dance, forming a new elliptical galaxy, sometimes referred to as Milkomeda. This collision will be a transformative event, reshaping the structure of both galaxies and igniting a burst of star formation as gas and dust clouds collide. Although such a cataclysm might sound destructive, the vast distances between stars mean that direct stellar collisions are unlikely. Instead, the merger will create tidal tails, intricate streams of stars, and a dramatic reshuffling of galactic components. Andromeda has been studied extensively using both ground-based and space-based telescopes. The Hubble Space Telescope has provided galaxy, revealing its intricate spiral structure, star-forming regions, and even individual stars. Future observatories, such as the James Webb Space Telescope and the extremely large telescope, promise to deepen our understanding of Andromeda by studying its stars, planets, and black hole in unprecedented detail. One of the most exciting areas of research involves the search for exoplanets in Andromeda. While detecting planets in another galaxy is extraordinarily challenging, advancements in microlensing techniques and spectroscopy may one day allow us to identify worlds orbiting stars in this neighboring galaxy. Such discoveries could revolutionize our understanding of planetary systems and the potential for life beyond the Milky Way. Andromeda's proximity makes it a valuable reference point for studying galaxies throughout the universe. By examining its structure, composition, and dynamics, astronomers can develop models that apply to galaxies billions of light years away. The study of Andromeda's dark matter halo, for instance, has implications for understanding the mysterious substance that makes up 85% of the universe's mass. The galaxy also serves as a time capsule, preserving evidence of past stars torn from satellite galaxies crisscross Andromeda's halo, offering clues about its history of galactic cannibalism. These remnants of past mergers help astronomers reconstruct the timeline of Andromeda's growth, providing a glimpse into the life cycle of galaxies. Beyond its scientific value, the Andromeda galaxy has captured the human imagination for centuries. Visible to the naked eye as a faint smudge in the night sky, it has inspired countless myths, artworks, and dreams of intergalactic travel. As our technology advances and our understanding of the cosmos deepens, Andromeda remains a symbol of humanity's insatiable curiosity and our quest to comprehend the universe. Whether through the lens of a telescope or the imagination of a dreamer, the Andromeda galaxy invites us to ponder profound questions about our place in the cosmos. What stories do its stars tell? What secrets lie hidden within its vast expanse? And what future awaits as our two galaxies converge in a cosmic embrace? The Andromeda galaxy, or Messier 31, stands as one of the most intriguing and vital cosmic neighbors of the Milky Way. Its staggering proximity of 2.5 million light years allows astronomers to explore galaxies across the universe. This massive spiral galaxy, over 220,000 light years in diameter, surpasses our own Milky Way in size and contains an estimated 1 trillion stars. Its colossal mass and dynamic nature make it a perfect laboratory for studying galaxy formation, star evolution, and the mysterious force of dark matter. Andromeda's double nucleus, a feature visible in its central bulge, has perplexed scientists for decades. This peculiar structure hints at a complex history of mergers and interactions with smaller galaxies. At its core lies a supermassive black hole, approximately 140 million times the mass of the Sun. This black hole exerts a gravitational pull that influences the orbits of nearby stars and triggers high-energy phenomena, such as X-ray flares. These intense bursts of radiation illuminate the dynamic and sometimes violent processes that occur in galactic cores. Clouds collapse under gravity to form new stars. Bright blue clusters dot these arms, signifying the presence of massive young stars that shine intensely before exhausting their fuel and ending their lives in driving the chemical evolution necessary for the formation of planets and potentially life. The interstellar medium of Andromeda is also rich with hydrogen gas and cosmic dust, creating vibrant nebulae that serve as the birthplaces of new stars. Unlike our Milky Way, which exhibits a more subtle spiral pattern, Andromeda's arms are well defined, giving it the iconic shape often associated with galaxies. These arms are not static. They are shaped and reshaped by the gravitational interactions with Andromeda's satellite galaxies. Observations reveal that Andromeda is surrounded by a swarm of smaller galaxies, some of which are being torn apart by its gravitational pull. These interactions create streams of stars, known as tidal tails, that arc through Andromeda's halo, providing clues about its history of mergers and acquisitions. Andromeda is not only a showcase of stellar life and death, but also a treasure trove of ancient stars. Its halo contains some of the oldest stars known, remnants from the earliest epochs of galactic formation. By studying these ancient stellar populations, scientists can trace the history of Andromeda back billions of years, uncovering the conditions that prevailed when the universe was young. These studies also shed light on the processes that shaped our own galaxy, offering a broader context for the evolution of the cosmos. One of the most captivating aspects of Andromeda is its future collision with the Milky Way. Observations of its motion indicate that it is hurtling toward us at a speed of approximately 110 kilometers per second. In about 4.5 billion years, the two galaxies will collide and merge to form a new, larger galaxy. This event, often described as a galactic dance, will dramatically reshape the structure of both galaxies. Stars, gas, and dark matter will be redistributed in a complex interplay of gravitational forces, creating tidal streams and igniting bursts of star formation. Despite the seeming violence of such a merger, the vast distances between individual stars mean that direct collisions between them are unlikely. Instead, the merger will create a new cosmic entity, sometimes referred to as Andromeda, with an elliptical structure and a new center of mass. The Andromeda galaxy has been the focus of numerous scientific missions and observations. The Hubble Space Telescope has provided some of the most detailed images of its structure outer halo with stunning clarity. These observations have not only deepened our understanding of Andromeda, but also serve as a benchmark for studying other spiral galaxies in the universe. Advanced instruments such as the James Webb Space Telescope promise to unveil even more secrets, allowing astronomers to study the galaxy's individual stars, planetary systems, and even its dark matter halo with unprecedented precision. The search for exoplanets within Andromeda is a burgeoning field of study. While detecting planets in another galaxy is extraordinarily challenging, techniques such as gravitational microlensing offer a glimpse into this possibility. These methods rely on the bending of light caused by the gravitational field of a planet or star, revealing the presence of celestial objects that would otherwise remain hidden. Discovering exoplanets in Andromeda could revolutionize our understanding of planetary formation, potentially revealing worlds vastly different from those in the Milky Way. Andromeda's immense halo of dark matter extends far beyond its visible disk, influencing the motion of its stars and satellite galaxies. This unseen component constitutes the majority of the galaxy's mass, yet its nature remains the greatest mysteries in astrophysics. By studying the distribution and behavior of dark matter in Andromeda, scientists hope to unlock the secrets of this enigmatic substance, which plays a crucial role in the formation and evolution of galaxies throughout the universe. As the largest galaxy in our local group, Andromeda serves as a cosmic mirror, reflecting the processes that govern galaxies on larger scales. Its intricate structure, active star-forming regions, and dynamic interactions with other galaxies provide a microcosm of the universe's complexity. By studying Andromeda, astronomers gain insights into phenomena that apply to galaxies billions of light years away, bridging the gap between our local universe and the distant cosmos. The Andromeda galaxy is not just an object of scientific inquiry. It is a source of inspiration and wonder. Its visibility to the naked eye as a faint smudge in the night sky has captivated observers for centuries, from ancient astronomers who cataloged it as a nebula to modern scientists who unravel its mysteries with cutting-edge technology. Andromeda represents humanity's enduring quest to understand the cosmos, a testament to our curiosity and imagination. The Andromeda galaxy is a beacon of cosmic curiosity, continuously drawing the gaze of astronomers and dreamers alike. Its vastness and complexity defy easy understanding, inviting deeper exploration with every new discovery. This galactic giant is not just a collection of stars, gas, and dark matter. It is a storybook of the universe itself, containing chapters that span billions of years and countless transformations. The study of Andromeda has provided humanity with unparalleled insights into the life cycles of galaxies. Its close proximity makes it an ideal target for research, as we can observe its individual stars and clusters with remarkable clarity. Scientists have identified diverse stellar populations within Andromeda, each with unique characteristics and histories. From the bright, young blue stars of its spiral arms to the ancient red stars in its halo, every stellar population tells a different part of the galaxy's story. These stars are not just cosmic objects. They are timekeepers, offering clues about the conditions that shaped Andromeda over its lifetime. Andromeda's history is written in the light of its stars, but it is also etched surround it. These tidal streams are the remnants of smaller galaxies that were torn apart and absorbed by Andromeda's gravity. By mapping these streams, astronomers can reconstruct the galaxy's dynamic past, piecing together the cosmic interactions that have shaped its structure. Each stream represents a merger, a collision, or a gravitational tug-of-war that occurred millions or even billions of years ago. They form a mosaic of Andromeda's evolutionary journey, providing a glimpse into the violent processes that drive galactic growth. The role of dark matter in Andromeda's formation and evolution cannot be overstated. This invisible, enigmatic substance makes up the majority of the galaxy's mass, yet its true nature remains one of the greatest unsolved mysteries in modern science. Dark matter does not emit or absorb light, making it undetectable through conventional means. However, its presence is inferred from its gravitational effects on visible matter. In Andromeda, dark matter forms an extensive halo that stretches far beyond the galaxy's luminous disk, influencing the motion of its stars and satellite galaxies. By studying the distribution matter in Andromeda. Scientists hope to unlock clues about the fundamental composition of the universe itself. Andromeda's future is as fascinating as its past. The impending collision with the Milky Way is not just an event of local significance. It is a cosmic spectacle that will reshape the local group of galaxies. This merger will occur over billions of years, beginning with subtle gravitational interactions that will distort the shapes of both galaxies. As the two spiral galaxies draw closer, their stars will form tidal bridges, connecting the two systems in a gravitational embrace. Gas clouds will collide, triggering bursts of star formation and creating brilliant nebulae that will light up the night skies of any planets within these galaxies. Eventually, the two galaxies will merge into a single massive elliptical galaxy, a testament to the transformative power of gravity on cosmic scales. While the prospect of this collision may seem daunting, it is a reminder of the dynamic and ever-changing nature of the universe. Galaxies are not static islands of stars. They are constantly interacting, merging, and evolving. The Andromeda Milky Way collision will not only reshape the structure of these galaxies, processes that drive galactic evolution. For astronomers billions of years in the future, this event will be a natural laboratory for understanding the interplay of gravity, dark matter, and interstellar gas. The Andromeda galaxy has also inspired humanity to think beyond our own cosmic neighborhood. The possibility of life in Andromeda, while purely speculative, raises profound questions about the nature of the universe and our place within it. If planets orbit stars in Andromeda, and there is no reason to believe they do not, then the potential for life beyond the Milky Way becomes a tantalizing prospect. While the vast distances between galaxies make direct exploration unlikely for the foreseeable future, the study of Andromeda fuels our imagination and drives the development of new technologies that may one day bring us closer to answering these profound questions. Telescopes have played a crucial role in our understanding of Andromeda, transforming it from a faint smudge in the night sky to one of the most studied objects in the universe. Ground-based observatories equipped with advanced adaptive optic systems have provided detailed views of the galaxy's structure, while space-based breathtaking images that reveal its intricate beauty. These observations have not only deepened our understanding of Andromeda, but also serve as a benchmark for studying other galaxies. By comparing Andromeda to galaxies at various distances, astronomers can piece together a timeline of cosmic history, tracing the evolution of galaxies from the early universe to the present day. Andromeda's spiral arms, central bulge, and halo are all areas of active research, each offering unique insights into the workings of galaxies. The spiral arms are regions of intense star formation, where massive stars light up the surrounding gas and dust, creating some of the most beautiful dynamic regions in the galaxy. The central bulge, by contrast, is dominated by older stars, providing a window into the galaxy's past. The halo, with its sparse population of ancient stars and globular clusters, represents the remnants of Andromeda's earliest epochs, a fossil record of gases that shape this distant galaxy are at work in the Milky Way and countless other galaxies. By studying Andromeda, we gain a deeper understanding of our own galaxy, our place in the cosmos, and the forces that govern the universe. The Andromeda galaxy stands as a pillar of scientific curiosity and inquiry, revealing profound truths about the universe's structure and evolution. Each observation, each analysis of this celestial neighbor deepens our understanding of the intricate forces that shape galaxies, including our own Milky Way. Scientists and astronomers have spent decades unraveling its mysteries, from its unique physical characteristics to the secrets hidden in its dark matter halo, which stretches far beyond its visible edges. To expand the horizon of understanding Andromeda, we delve even deeper into the vast scientific details that define this monumental galaxy. One of the key features of Andromeda is its massive dark matter halo, a structure so vast and diffuse that it dominates the dynamics of the galaxy. Observations suggest that this halo extends hundreds of thousands of light years beyond the galaxy's luminous disk. disk, encompassing both its satellite galaxies and intergalactic space. Unlike the stars and gas within the galaxy, dark matter does not interact with electromagnetic forces, making it invisible to telescopes. However, its gravitational effects are profound. The motion of stars in Andromeda's outer regions can only be explained if we account for the gravitational influence of this unseen mass. The study of Andromeda's dark matter halo has significant implications for cosmology. By measuring its distribution density, astronomers can test theories about the formation of large-scale structures in the universe. The presence of such a massive halo supports the lambda CDM, lambda cold dark matter model, which posits that galaxies form within vast, invisible scaffolds of dark matter. Furthermore, detailed mapping of Andromeda's halo through gravitational lensing and stellar dynamics provides clues about the nature of dark matter particles. One of the most elusive questions in modern physics. Another remarkable aspect of Andromeda is its double nucleus, a feature that has fascinated scientists since its discovery. This central region is that one of these clusters represents a dense group of stars surrounding Andromeda's supermassive black hole, while the other is a remnant of a smaller galaxy that merged with Andromeda long ago. This unusual configuration offers a unique opportunity to study the dynamics of galactic nuclei and the behavior of stars in extreme gravitational environments. The supermassive black hole at the center of Andromeda is estimated to be about 140 million times the mass of the Sun, significantly larger than the black hole at the center of the Milky Way. This immense gravitational powerhouse shapes the orbits of stars within the galaxy's central bulge and influences the flow of interstellar gas. Observing the interactions between this black hole and its surroundings provides critical data for understanding the growth and evolution of supermassive black holes across the universe. These observations also help astronomers explore the relationship between black holes and their host galaxies, a fundamental question in astrophysics. Andromeda satellite galaxies add another layer of complexity to its story. These smaller galaxies, such as M32 and M110, orbit Andromeda in intricate patterns, influenced by its massive gravitational pull. of being torn apart. Their stars and gas streams forming tidal tails that arc across the sky. These interactions offer a glimpse into the hierarchical nature of galaxy formation, where larger systems grow by accreting smaller ones. By studying these satellites and their interactions with Andromeda, scientists can reconstruct the galaxy's merger history, tracing its growth over billions of years. The star-forming regions within Andromeda are particularly noteworthy for their scientific importance. These areas, known as HII regions, are dense cloud ionized hydrogen where new stars are born. Observations of these regions valuable insights into the processes that govern star formation, such as the role of magnetic fields, turbulence, and feedback from massive stars. The distribution and intensity of star-forming regions within Andromeda's spiral